Hello बच्चों, Sat Sri Akal and Namaste from my side. So this is a teaser of what content we are going to study in this lecture. Projectile motion, riverman problems, uranium deposits, uniform circular motion of an electron, non-uniform circular motion, Riemann problems, the lecture of motion in the 2D is loaded. So, students, this was a teaser, right? Of, as usual, what we are going to study, right? The content we are going to study into the most innovative way in this lecture. Right? Tank and Riverman and Rainman and all of those stuff. So, are you all ready? Let's start with. Hello, bacho. Sat Sri Akal and Namaste from my side. How are you all? So this is your own physics educator Indrajeet Singh welcoming you all onto the most sensible platform of an EdTech. Right? For an aspirants, those who are preparing for the JEE and NEET kind of the competitive examinations, as PW is a box of surprises, we are growing high and high. Right? Lots of domains, right? They are getting introduced in our space, okay, in our EdTech space, like PhysicsWallah, foundation, and lots of things, right? Now we are moving on towards the boards, okay? So as everything for you all, right? Our team for you all. So guys, let's move on to the most important stuff for today's lecture, that is motion in a 2D. Champion series, right, has already 2 lectures uploaded, right? For the first, the first was of the units in measurement, second was for motion in 1D. In motion in 1D, I clearly mentioned, right? In motion in 1D, I clearly mentioned about this stuff, right? We are not going to deal with the cause of the motion because we are right now dealing with the kinematics. And kinematic itself states that what, right? We are not going to deal with any cause. But just keep one thing in your mind, that we are going to deal with the acceleration. We are going to deal with the how acceleration is going to change the velocity of a specific particle. But obviously we are not going to deal, right? Extremely sorry. We are not going to deal with any kind of the force right now, right? Okay. In some cases of the projectile, right, there is a possibility that my angular momentum and this kind of stuff may come, but it will be for a very short period of the time, and I will explain like that way that you will immediately grab that concept. Okay, so motion in 2D reality disclaimer. Today Indrajeet sir is going to come into the visualizations, right? Lots of visualizations we are going to see related to the all of the motions into the 2D, right? And Indrajeet sir himself is going to come and deliver you all stuff. Okay, so reality disclaimer. Thousands of times we played a cricket, but we never thought of, right? Thousands of times you have played the games of the Angry Birds, but we never thought of, right? Thousands of times, right? We have played the game of cricket. Cricket is like what we can say, okay? I must say there exists like maximum number of the students has played cricket in their entire, right, span of the, what we can say, in entire childhood. They have played, but we have never thought of, right? We have never thought of that it is a kind of a motion in a 2D, right? Thousands of times we have played this kind of game. You can see into this visualization that this Angry Bird is going to hit some specific target, right? The Angry Bird is going to hit some specific target. Thousands of times we have played this game. Even this game gone viral when it was like published on the web platforms, right? It went viral. right? But we never thought of how we can correlate the projectile to the example of the Angry Birds. How we can correlate the projectile to the right example of the Angry Bird. So that's in reality disclaimer with the teaser in front. Okay, so now today we are going to like have a most what we can say the useful stuff. Now let's see how we can go to okay motion in 2D, right? In this lecture we are going to deal with some of the important concepts, right, of the projectile motion, right? Some of the important cases of the projectile like the horizontal projectile motion and projectile motion of the inclined plane. In all of those concepts directly, right, see, we are going to see what actually concept says, right, what it states, and question solving approach, right, and PYQs. This will be the sequence of the chapter as we are following into the previous one. This sequence we have followed into the previous one also, right? First, what you have to move on, we will move on actual to the like basics of this specific topic, and then I will show you all the actual question solving approach from which the JEE and NEET kind of the sums, right, the PYQs, how we can solve, right, the PYQs using that question solving approach, right? And after that we are going to see some PYQs. So first, projectile. Second, some of the cases like horizontal projectile motion in an inclined plane. We are going to deal with the stuff of the circular motion, relative motion, 1D and 2D. In a previous lecture I already told you all, right, we have kept apart, right? Okay, what we can say, I told you all that we are going to discuss relative 1D and 2D, right, okay, together in this session, and that we are going to do. Okay, after that we are going to see the Rainman problems, and finally the Riverman problems and the relevant PYQs. So this is the stuff what we are going to discuss in this lecture. Now, what will be the flow chart of this session or this specific chapter? So let's move on. If I'm talking about the motion in 2D, right, if I am talking about the motion in 2D, right, then obviously the first bifurcation of motion in 2D, right, it is going to be projectile, right? Okay, projectile, it means first we are having oblique projectile motion, right? Second, we are having horizontal projectile motion, right? Third, we are having inclined plane projectile motion, right? And apart from this, some of the important cases of the, right, okay, projectile motion, some of the important cases and examples related to this projectile motion. So the first bifurcation of the motion into the 2D, it is directly moving on to the projectile. Okay, now what about the second bifurcation? Okay, what about the second bifurcation? It is directly moving on to the part of kinematics 2D. Like we have seen, right, the three equation of the motion. See, whenever the acceleration of the particle is constant, right, then we have already seen the three equations of the motions into the, right, the three equations of the motions for the particle, like V is equal to U plus AT, S is equal to UT. That thing we are going to see into the 2D form, right, like vectors and equations. What kind of the equations when acceleration of the system is kept completely constant? Vectors and equation. What kind of the equation, right, in which the system is kept completely constant, right? Okay, and some of the important parts are related to it. Apart from this, right, we are going to discuss obviously the concepts of the circular motion. In circular motion, right, we are going to deal with the stuff, right, of first uniform circular motion, right, second non-uniform circular motion, and some of the important concepts related to it. What is a centripetal? Apart from this, there exists a third topic, that is motion in vertical circle, right? But this concept involves, right, the cause of the motion, right? This concept involves the motion into the vertical circle involves the, right, force. So that's why we are not going to discuss it as right now, right? We will discuss that stuff into the work energy and power session, right? Okay, and the fourth bifurcation of this chapter directly moves on, right, to the concepts of the relative motion, right, and the applications of the Riverman problem and the Rainman problem. If I'm talking about the Rainman problem, right, and second Riverman problem, right, aeroplane wind, These are also known as aeroplane wind problem, right? This is also known as sometimes scarf flag problems, right? This all are the applications of the relative motion, right? And today we are going to discuss the relative motion in 1D and 2D both, right? In 1D and 2D both. So this is what the bifurcation of the motion into the two dimensions it is. Right, this is what a bifurcation, right? I'm moving aside. If you all want to take a snap, you can just have a snap, right? I'm giving all the 5 seconds. You can even pause the video, right? Or you can have a snap of it, right? So it's 5, 4, 3, 2, 1. That's it. So this was a motion in a 2D. Now let's move on to the next part. Let's begin this session. Let's begin this session with the concepts of the projectile motion. Let's begin this session with the concepts of the projectile motion. What it states. See, right now I'm not moving on to the projectile motion. It means that, sir, this the object following this kind of the trajectory, then we can say it is a projectile motion. No. Fundamentally, first of all, we will define the actual definition what its projectile states according to the NCERT. The page number is written according to the NCERT, page number 77. The most basic definition, right? What is a projectile? After that, we are going on to some cases, the classification of the projectile like oblique, horizontal and inclined plane, and what is the difference? What is an actual difference between them, right? Okay, in conceptual terms, right? So what is the just right now we need to move on to the concept of the projectile motion. Now, what is a projectile? An object that is in flight after being thrown or projected. That is projectile, right? In some of the resources, right? In some of the books and resources, motion under gravity, it is also given the name as projectile. Whoa, sir. That's a shocking thing. How motion under gravity is a projectile. If you can see in some of the sources now in the relevant examples it is written. Suppose if the ball is thrown with some speed and it is following this, like it is thrown upwards. Let us take an example. A ball is thrown with 20 meters per second upwards from the ground. Now it return in what time, right? What will be the time of the flight of the projectile when it will return back to the ground? Right? What is the time of the projectile, right? So projectile itself doesn't mean this kind of a trajectory or horizontal motion kind of a trajectory. No. Projectile is having the simple definition. Object thrown, right? And it is in the flight. Object that is in flight after being thrown. Right? Now let us take an example, right? I'm going to demonstrate one simple example that you have, right? Everyone, they have moved on into their childhood. Right? Suppose let us take an example, right? See, faculty is offline classes going on, school classes are going on, right? Simple, very simple, right? And okay, you can even imagine it easily, right? Okay, the lecturer, right? Your teacher is like explaining the stuff on the board and writing something, okay? Writing some content, okay? Immediately the backbencher is trying to misbehave, okay? So teacher immediately got what we can say, right? She turned out immediately by hearing the voice, right? Okay, of getting misbehaved, and she throwed a chalk, right? Like this way. See, you can just. What happened here, right? I'm just demonstrating it again, right? I'm demonstrating it again, right? Okay, see what happened here. You saw now the chalk followed a specific trajectory. That is projectile, right? Object was in the flight now and it was thrown. It is a projectile. Suppose this is an object, this is thrown into the upward direction. Yes. And it is moving back, coming forward, like it is reaching to the maximum height and coming back towards the right to the original, to its original position. Right? Then this is also when the object was thrown, it was in flight. So this is also the projectile. Projectile it is not bounded by only one simple term like this way. No. Have you ever seen into the war films, border, right? The firing of a tank, right? Cannonball firing, right? Okay, see, let us take in a very simple example, right? Okay. Chalk thrown by teacher It is an example of the projectile. Second, tank fire, right? It is an example of the projectile. Man kicking a football. It is an example of the projectile, right? But it is following some kind of the trajectory. It is a projectile. And generally, I'm talking about it. I'm not moving on. I'm not keeping all of those right concepts into the foundation, right? I'm just explaining into the generalized form that what actual the projectile is. Let us take in another fourth example, right? But it is also the projectile, right? Okay, because mom hand was in a flight for you all. Okay, but this is not actually what we can say the correct example of the, it is one of the, but not actually, right? Okay, the correct example. Okay, so it was just for the fun. Okay, chalk thrown by a teacher, tank fire, cannon, ball fire, right? This is also the one of the examples of the projectile. So this is what given into the NCERT, right? Not what I am delivering in front of you, right? Okay, this is not what I am delivering in front of you, right? So the first, it is an actual definition of the projectile. Object thrown, it is in the flight. Okay, that is a projectile. See, no discussion about the gravity, no discussion about the gravitational acceleration, how it is acting, right? Like that it is going on. No, just a projectile. Now, after this, the projectile is having the three kind of the classification. Among them, the first one is the oblique projectile. The second one is a horizontal projectile motion. The third one is inclined plane projectile. Right. These are the three different ways how particle is thrown, right? And three different kind of the trajectory particle is following. Again, I am repeating my statement, right? Okay, we already discussed about what actually the projectile is, right? But these are the three cases or the three different ways of how the particle is thrown, and it is following the three different kind of the trajectories, and we are going to analyze those trajectories and obtains the relevant and needed formulas, okay, to the concept. So three kind of the projectile motion. The first one, that is an oblique projectile motion. See, you can see the visualization, right? The tank fire, right? You have seen our great, right, Salmon Bhai. Okay, you have seen our great Salmon Bhai into the race 3, right? That equipment he was having, na, right? And he was just firing. Na. So he was like, he was holding that stuff like this way. He was holding the equipment like this way, right? But it followed this straight trajectory. No, it actually needs to follow this kind of the trajectory. But that is also the projectile, right? Race 3, right? Lots of viral stuff, right, regarding this concept went on when the trailer was released. Okay, so you can see this is a visualization. That's demo. It's clearly states what actually the oblique projectile. We are going to discuss into the detail, right? But we will see the visualization should be there in front, right? With visualizations, right, physics is quite easy to understand. See, you can see this is the oblique. Now, suppose a war is going on, plane is moving at some specific height with respect to ground, right? And the plane is dropping the bomb. Okay, then one specific trajectory, right, the particle is in flight for a time, it was thrown by the plane, so that is a projectile. Inclined plane projectile, right? Okay, inclined plane, suppose let us take an example with respect to the ground. Okay, the surface is inclined, and the particle is thrown from the bottom to top to bottom, right? Then it is following some specific kind of the trajectory, that is also known as the inclined plane projectile, right? So first we moved on to the what actually the projectile is, right? Okay, no caste, no discrimination, there is something like that. After that we moved on to the classification of the projectile. Now we are moving on to see we have to deal with right, theoretical physics, right? This is not a practical physics, this is not a practical demonstration going on, right? We are moving on to some theoretical part of the physics. So for that we need to take some assumptions. Now, what kind of the assumptions? In my previous sessions also I told you about, right, motion without frame of reference is not possible, right? Motion without frame of reference is not possible. If any activity is going on, then there is always an observer to analyze it, Again, I'm repeating that statement. If any activity is going on into the surrounding, then there is always an observer. There is always a frame of reference, right? And if frame of reference changes, right, things get changed, physics get changed, right? Suppose let us take an example. If I recently I gave you the example of, see, again I'm demonstrating that stuff, right? Okay, see, teacher in the class, someone misbehaved, right? Teacher threw the chalk. Is it possible, right, that air is absent here? Practically I'm talking about. Is it possible that air is absent? No, practically it is not possible because we are not in vacuum, right? We are not in vacuum. Okay, so the first assumption, see, we are moving on to the theoretical part. So the first assumption, right, air resistance is always absent. We are going to discuss that concept also, that stuff also, in which we will consider, right, okay, we will consider the presence of air resistance. But the initial basis, the beginner's level, right, we need to consider air resistance as absent. Second, effect due to the curvature of the earth, right? Generally, in all of those reference books, it has been taught that whatever the motion of the projectile it is going on to nearer to the surface of the earth, right? And as because of the whatever the curvature of the earth is there, okay, there is a variation in G, variation into the gravitational acceleration of the earth, right? Right. So in summarized form, that variation we can't, what we can say, we can't we need to avoid all of those variations. We can't afford it. We can't afford the variations of the values of the gravitational acceleration apart from, right, 9.8 to 10, right? So with respect to height, with respect to depth, all of those earth factors we are completely avoiding, right? We are avoiding the air resistance, the presence of air resistance. We are avoiding all the earth related factors, right? See, the rotation of the earth, curvature of the earth, air resistance is always absent, right? Okay, and the projectile is always thrown. Okay, this is the most important stuff, and that you are going to discuss, right? We'll discuss this stuff into the gravitation chapter, okay, in the concepts of escape speed and escape velocity and interstellar speeds. Whenever the object is thrown, right, more than the speed of 11.2 km per second, obviously it is going to escape from the gravitational field of the earth. It is going to escape from the gravitational field of the earth. It is, right, one and the sure thing. Okay, so for that reason, whatever the examples we are going to discuss into the projectile, all will have the speed less than the escape speed of the earth. So these are the assumptions, right, that we are going to take before discussing on to the concepts of the projectile motion, right? So you can just grab the flow of this chapter. First we discussed on to the NCERT definition of the projectile motion, then we moved on to the classification of the projectile motion, then we moved on to the assumptions of it. Now we are finally moving on to the first case of the projectile motion, right, and that is a oblique projectile. And see, Indrajeet sir is there in front of you all, right? And this is just such a simple example, right? Okay, I'm going to demonstrate one simple, see, whatever it is there in front, I'm going to demonstrate in front of you all, right? Just I'm going to demonstrate. You need to just give me a second, right? See, I'm showing you all, see, I'm having a ball in front, right? Okay, see, same example, like this way. I'm throwing the ball. You can see, object is thrown, right? You can see, you can just check it out. Object is thrown like this way. Okay, again I'm throwing, object is thrown, right? Okay, so this example, what it's demonstrate, right, what it states, when object is thrown, see, this is a horizontal level. When object is thrown at some angle with some respective velocity, then it follows a specific trajectory, right, with respect to the person on ground. This kind of the motion, it is known as oblique projectile motion, right? The one example we are going to take, and we are going to understand the concepts up to the advanced level for the projectile motion. The same example, only one example. This Indrajeet sir will be present like this way till end. Okay, Indrajeet sir will be present like this way till end, right? Okay, the same example, okay, and we are going to discuss it. And see, let us again see, I have thrown the ball. Can I say this is a ground? Right, with respect to the ground, right, particle is thrown with some speed u at some angle theta, right, then it is following some specific kind of the trajectory, right? This is the oblique projectile. This is the oblique projectile. Okay, see, we are not going to see, right, this projectile motion into the regular format. No, right, today we are going to change the format, right, to understand this stuff into the quite convenient manner, right? What actually it is, see, if I'm talking about the velocity, can we break the two component of the velocity? This is the first component and this one is the second component. This one is the first component of the velocity and this one is the second component, u sine theta, right? The first component and the second component of the velocity. What actually the motion in 2D means? 2D, see, 2D, it means combination of two 1D kind of phenomena. Okay, two 1D kind of phenomena, right? They are giving the resultant of 2D, right? Either this 1D phenomena is going on to the x-axis, y-axis or z-axis. Either this another phenomena is going on x, y or z. Two 1D combines to form 2D. 3 1D combines to form 3D. Have you ever thought of why there was a need of a vector? Have you ever thought of why vector was introduced? Why there was a need of a vectors? In entire universe, not only one dimension activities or phenomena are going on. In entire universe, right, the entire universe is divided in approximately 11 dimensions, right? Lots of assumptions and theories are there. Okay, string theory is there and relativity and lots of contradictions are also there. We are not going into that detail manner, right, into that in that much detail about that part, but the entire universe, let us take an example, it is divided into the 11 dimensions, right? But right now we are only aware of the 3. The fourth one is just yet, okay, it was yet just introduced, right? Okay, and it was a time. So if we're talking about only the phenomena, see, lots of phenomena are going on into the surrounding, into the space, into the 3-dimensional space, right? So those phenomena, right, they are not only in 1D, okay? So to analyze all of those activities into the multiple dimensions, the vectors were introduced. I'm giving you all the example in front. Let us take an example, right? This is a runway, right? If the aeroplane is moving, I'm not having the time to draw it. Before takeoff, it is moving. So it is moving onto the straight line. So that is an example of motion in 1D. Right? Plane is, right, moving before takeoff, right? It is gaining some speed and momentum, right? Okay, for takeoff. So that is an example of 1D. When it takes off, right? Something, when it takes off, right? It is moving forward also. It is gaining some height also. Right, before taking off it was just moving forward, so that's why it was an example of 1D. Now at the moment it is getting takeoff, right? So it is moving forward also and it is gaining some height also. The first 1D motion, it is in the forward direction. The second 1D motion, it is in like gaining some height into the vertical direction. So the combination of the horizontal and vertical, we are having the resultant, and that is a motion in 2D, and it results as plane is taking off. Something the plane is contributing into the horizontal, something the plane is contributing into the vertical, whatever the resultant. Now see, two 1D phenomena are going on. One, it is going on into the x direction, one is going into the y direction, right? So I can't algebraically result them. So for that reason, vector was introduced, right? we can have the vector resultant of one motion in the x direction, motion into the y direction, right? That results the motion in 2D. Okay. So runway, before taking off, right, when the plane is gaining some momentum on the runway 1D. Now plane is taking off, so it is moving in forward direction also, and it is gaining some height also. So the resultant of this two, it is 2D. Now after taking off and gaining some height, right, it is changing its direction like this way also. That is 3D. It is moving forward also, gaining some height also, and turning also. Moving forward 1D. Moving forward also, gaining some height also, 2D. Moving forward also, gaining some height also, and turning also towards specific direction, 3D. So this is what the best example. Why I demonstrate this stuff in front of you all, right? Because we are going to analyze the projectile, right, as a combination. See, this is a motion into the 2D, right? So we are going to separate that stuff. Okay, something, can I say projectile, right, into the vector form, something that is contributing into the horizontal direction and that is represented by I, plus something that is going to contribute into the vertical direction and that is represented by J. Projectile, right, something, this is a resultant, now this is a 2D. It is a resultant of two 1D phenomena. One 1D phenomena is going on into the horizontal and second phenomena it is going on into the vertical. The vector addition of this, it is going to result one 2D phenomenon, that is a projectile. Projectile, combination of horizontal plus vertical, right? The resultant of the vector resultant of horizontal and vertical. So that's why u cos theta, it is contributing, right, into the horizontal direction, u sin theta, right, this component of the velocity, it is contributing into the vertical direction. This is helping the particle to move forward with respect to the point of projection. This velocity is helping the particle to gain some height. One is helping the particle to move forward, one is helping the particle to gain some height. Right? Okay, so this is what actual, now what will be the nature? See, some 1D phenomena is going, some 1D motion is going on into the horizontal, some motion is going on into the vertical motion, in the vertical part. What will be the nature of that motion, we are going to analyze. So this was just about what actually the oblique projectile is. Now let's move on to the next part, the actual analysis. What will be the nature of the horizontal motion? What will be the nature of the vertical motion? How they are like vectorially they are added, and what results we are, right, having in front. Okay, so again, this is a ground. Okay, particle is thrown, right, with some velocity u. It is having the two component, one that is contributing into the x direction, second that is contributing into the y direction, right? Okay, now what will be the nature of the motion in projectile? Nature of the motion of the projectile. U cos theta u tan. See, as I said, projectile, it is a combination of something that is contributed into the horizontal part. I can represent it as a I, and something that is contributed into the vertical part, I can represent it as a J. Right? Now, see, as I said, air is absent. Right? This is one of the assumptions of the projectile motion. Na? So, there is no horizontal acceleration either into the opposite direction of the velocity, right, or into the, right, the direction of the horizontal component of the velocity. Horizontally, due to the absence of air, there is no acceleration. It means that there is no presence of acceleration, right, which is either increasing or decreasing this u cos theta of an object. Horizontally, there is no acceleration which is increasing or decreasing the u cos theta of the object. It means that if u cos theta, the horizontal component, the one of the motion, one of the components of the motion, right? It is constant. It means that the nature of the horizontal contribution is uniform. Nature of the horizontal motion, horizontal part of the 2D is uniform. Why? Velocity, the horizontal component, is constant. Why it is constant? Because air is absent, right? There is no presence of any acceleration. Either it is increasing or decreasing the velocity. So this was the analysis of the horizontal part. What will be the nature of the motion of the horizontal? That is uniform. Now, what about this u sine theta? How it is changing? If I'm talking, the particle is thrown. I throw that object at t is equal to 0, like this way. Right? Whenever it is reaching to the max height, right? Whenever it is reaching to the max height, right? We are only having the horizontal component of the velocity. The vertical component of the velocity completely get dispersed. Right? It get disappeared. Sorry. Right, it get disappeared. So it means that at t is equal to 0, we are having u sine theta. At a moment, right, we are having u sine theta value as 0. It means there is a presence of acceleration into the vertical direction that is increasing or decreasing the u sine theta, right? It means there is a presence of gravitational acceleration into the downward direction. U sine theta upwards, g downward. Acceleration and velocity, right, they are in opposite direction. For half of the path, right, this acceleration is in opposite direction of u sine theta, so it is going to decrease it. So that's why at this moment we are having the vertical component as u sine theta, and at this moment we are having u sine theta as 0. So from u sine theta to 0, right? Who is decreasing the vertical component of the velocity? G. Is this value constant? Yes, this value is constant, right, into the y direction. Right? It means if acceleration in y direction, see, there is no acceleration into the x direction, but the gravitational acceleration is present into the y direction. Right? And that is constant. And acceleration constant, it means that vertical motion is uniformly accelerated motion. X direction uniform, y direction uniformly accelerated, resultant of this two projectile, oblique projectile. Right? Okay. So this was the analysis, right? Okay, this was the analysis. Okay. So now let's move on to the next part. Okay. Question solving approach. What is the question solving approach of the oblique projectile? Right? It's simple. Okay. Projectile is a resultant of something that is contributed into the x direction. Right? That is a horizontal contribution. Okay. And that horizontal is a uniform if there is an absence of air, plus something that is going to contribute into y. This is the vertical motion, and this vertical is UAM. UAM stands for uniformly accelerated motion. The resultant of this two is projectile, right? Resultant of this two is projectile. This will be our question solving approach. We are going to see all of those stuff right into the vector form only, right? We are going to see all of those stuff into the vector form. Okay, again, see, okay, see, let's see first of all. Okay, we moved on to what actually the projectile is. Right? After that, we saw the classification of the projectile. Right? After that, we saw some of the assumptions related to the projectile. After that, we moved on to the concepts of the oblique projectile, what it states, how we can consider it as a 2D, how the vectors plays the important role, what will be the nature of the horizontal, what will be the nature of the vertical motion. Right? After that, we had a detailed analysis of it. Right? And we saw the question solving approach. Now we are going to deal with some of the parameters. Generally, when projectile is taught, first of all, trajectory equation is, first of all, time of flight is, right, is explained. After that, equation of trajectory is explained. After that, range is explained. After that, max height is explained. No, we are going to move on into the different manner, right? Because what stuff I'm going to discuss in front of you all, na, right? Today, that is really going to amaze you. Right? Into the different manner we are going to deal with the projectile. And I guarantee, right, that this concept is going to be into the roots, right? Into the roots of your, what we can say, you will easily grab that stuff and can store into the permanent memory of your brain, right? That's a guarantee. Right. So we are not going to discuss range of and time of flight, range, Mach height first. First of all, we are going to discuss time of flight, then some another parameters, right? Okay, and those parameters are really helpful for NEET and JEE kind of examinations, right? Time of flight. See, simple. Now you all are completely aware of this is ground, right? At t is equal to 0, right? Particle is thrown with some specific velocity at specific angle with respect to the horizontal, right? Okay, so this kind of the motion of the particle, it is a projectile now, right? What it states, right? What it states. See, everyone, those who are right, seeing this lecture right till now, see how we can calculate. Say t is equal to 0, right? The particle is thrown at some time t, it is hitting back to the ground, followed by some trajectory, right? So for a time, right, particle was in the air, right, before hitting the ground, that is a time of flight. Okay, for a time particle is in air before hitting the destination. Before hitting the destination, that time it is known as time of flight. Now see how to calculate it. When it hits the ground, actually the height is 0, right? Height of particle with respect to ground is 0 when it hits, right? When it hits, right? So it means that, see, the y component is 0, right? Y component is 0. So this is an actual concept. Just hold on for a while, right? We are going to come back here only. Okay, just hold on, right? We are going to come back here only. Okay, why? Because first of all, we need to move on to the position at any time instance, velocity at any time instance, right? Then we are going on to move on with the time of flight. Okay, see, suppose this is a ground. So this is a t is equal to 0 when particle is thrown at some specific speed with respect to theta at the ground, with respect to theta, right? Okay, on the ground. There are two components of the velocity, one that is contributing into the horizontal part, second that is contributing into the vertical part. Now, between t is equal to 0, to time of flight, the position of the particle is continuously changing with respect to time. Suppose let us take an example at t by 8th, particle is at this position. Suppose at t by 2, the particle is at this position. Suppose at t dash, the particle is at this position. Suppose at t double dash, the particle is at this position, right? So the position of the particle on the entire trajectory at specific instance of the time. The position of the particle on entire trajectory at the specific instance of the time. It is represented by a vector. Position of particle on trajectory is described by vector, and that is a position vector at any instance of time. So this is the instance of the max height time t by 2, this is a t dash, this is a t double dash, right? This is, let us take an example, okay, t by 8, something like that. How we are going to identify this stuff? See, This is R as a position vector. This is a position vector. Let us take an example. This is R1. This is a new position vector R2, right? Okay. So this is a final R3 position vector. Okay. With respect to the, see, this is a reference point, as I said, right? All of the motion we are analyzing with the reference point, and in maximum number of the cases, the reference point is t is equal to 0. With respect to the reference point, first position was like this way, then position was like this way, then vector moves on like this way, then vector moves on like this way. So everything we are going right with respect to the point of projection. So at any instance of time, right? At any instance, something into horizontal, something into vertical. It is moving forward also, it is gaining some height also. So something with respect to contribution in horizontal, something with respect to the vertical. Now, as we have seen before, what is a nature of the, what is a nature? See, position is defined as, right, this position vector at any instance, this will be Rx or Ry, right? If I'm talking about the horizontal part of the projectile, then the nature of the motion is uniform. So for uniform motion, how I am going to write the equation of displacement, velocity into time? The contribution of the velocity is u cos theta into the horizontal part into time. This is R of x. Plus, it is gaining some height also. The height is increasing till some specific part and then decreasing, right? So what is what component of the velocity that is contributing into the vertical? U sine theta. Who is going to increase and decrease that? This component G. G is constant. It is a uniformly accelerated motion. So uniformly accelerated motion, what was the equation of displacement? It was S is equal to ut plus half at square. That was the equation of the displacement, na? Ut plus half at square. What will be the u here? Vertical component of velocity. So can I write it as u sine theta into t? What will be half at square? What will be the value of the acceleration? G, negative into the downward direction. Half g t square of j. This is the position of the particle at any time instance. Right? This is the position of the particle at any time instance. Okay? Position of the particle at any time instance. Something that is contributing into the horizontal. What is the nature of horizontal? Uniform. So in uniform motion, what is the equation of displacement into the horizontal part? Velocity into time. Now, what component of the velocity that is contributing in horizontal? U cos theta. It means u cos theta into time, right? With this factor, particle is moving forward. What component of velocity that is contributing vertical? U sine theta, right? How height is changing, right? Okay, it is increasing and then decreasing, right? It means there is a presence of acceleration, G, and there is constant acceleration. It means uniformly accelerated motion. Now, how we are going to describe the height, the displacement for uniformly accelerated motion? S is equal to ut plus half at square. This is what, na? See, S is equal to ut plus half at square. U contribution into the y direction, u sine of theta, t. What is an acceleration? Negative of g, right? And t square. Why I said negative g? Because we already discussed the convention. Upward will be the positive, downward will be the negative. Right side we are having the positive I, left side we are having the negative I, right? Okay, the direction of the vector, the convention we are going to take. The direction of the vector and the convention we are going to take. Okay, so that's why I wrote this. So this was a vertical contribution. Okay, now another thing, it is also making some angle with respect to horizontal. See, this angle will be phi 1, this angle will be phi 2, this angle will be phi 3, this angle will be phi 4. Right? It is making some component, it is making some angle, na? Suppose if I am talking about this position, this is a position vector. So this will be the Ry and this entire thing will be the Rx, right? Okay, so what will be the angle? tan of phi. Let us take an example. This is phi. Angle is phi. So this will be y component by x component, the simple explanation of vector. Y component by x component, the simple explanation of vector. Right? With respect to time, x is changing. With respect to time, y is changing. With respect to time, angle is changing. Right? Okay. So this will be y u sine of theta minus half of gt whole divided by, right, u cos of theta. This is how angle is changing with respect to time. This is how position is changing with respect to time, right, with the use of something that is contributing in horizontal, something that is contributing in. Many, those who have seen this lecture till now, many are having the questions in their mind. How? Why you are representing this position at time t right now, instead of moving on to the very fundamental concepts of range, time of flight, maximum height and everything. There is some reason behind it. Okay, first of all, just allow me to complete the position we have seen. We are going to see the velocity at time instant, right? After that, you will immediately get a click why I did that first. Immediately. Ground. T is equal to 0. Particle is thrown with some speed, something that is contributing into the horizontal, u cos theta. And this is u sin theta. Velocity is tangent to a trajectory. Velocity is a tangent drawn on trajectory. Right? Tangent drawn on a trajectory. Suppose if you want to, let us take an example. This is point A, this is point B, this is point C, and this is point D. Right? Particle is moving from t is equal to 0 to time of flight t. In the entire trajectory, I want to identify the velocity of the particle at any time instance. So it is always a tangent drawn right on a trajectory. See, suppose if I want to identify the velocity here, this will be the velocity right at A. This will be the velocity at B, right? Okay, this will be the velocity at C, and this will be the velocity at D. Okay. Again, it is a vector, so we can break it into the two components. This will be UA cos of phi, right? This will be the vertical component UA sine of phi, right? Similarly here, we can say UC, right, sine of phi 1, UC cos of phi 1. So this is how, see, velocity is changing like this way. You can just check it out. Again, I am showing you, I am demonstrating in front of you all. Initially, the vectors is like this way, resultant is this. Vectors are like this way, components are like this way, resultant is this. Right? Now, vertical component of the velocity is going to decrease slowly. When we are reaching at the max height, we are having only horizontal component. Now, slowly, right, the vertical component is increasing. Like this way, the vector is getting changed. So what will be the velocity at A? What will be the velocity of B? What will be the velocity at C? What will be the velocity at D? Right? It should be there, na? It should be there. Anna, it can be asked into the examination, na? We are in need of a general equation. So obviously, how to determine the velocity at time t? Something that is contributing in x with respect to time, something that is contributing in y. What component of the initial velocity that is contributing in x? U cos theta. What is the nature of horizontal motion? Uniform. It means u cos theta is constant. It is not going to change with respect to time. So this will be the horizontal part of the velocity. Right? Horizontal is a uniform, na? So it's a u cos theta. Okay. U sin theta, right? G is into the opposite direction of the u sin theta. So till half of the trajectory, G is going to, right, decrease the u sin theta, and then G is going to increase the u sin theta. right? So it means that u sin theta is changing, u cos theta was not changing. That's why I kept this horizontal component of velocity at any time as constant. And even the nature of the horizontal part is also the uniform. But if I'm talking about the vertical g is there, this is constant acceleration. It means it is a case of uniformly accelerated motion. For uniformly accelerated motion, right, the equation of the velocity is written like this way. But how we are going to write this stuff for the y part? V of y, that is u of y minus acceleration of y into t. So v of y, that is u of y was u sine of theta minus gt. Why I am taking g as negative? Because it is directing downwards towards the negative j direction. You can see this analogy, na, right? This we have already seen into the third chapter. So v is equal to u sine theta minus gt. This will be the vertical component of the velocity, and this is the equation of change of the velocity on entire trajectory with respect to time. That's why I moved on to why I separated the horizontal and vertical and the vector addition, giving the resultant as a projectile y. Okay, now we are going to reveal in just short period of time. Okay, now see what angle it is making with, see, if I'm talking about the trajectory na, then position vector makes angle with respect to horizontal ground. Similarly, the velocity is also making this angle. Suppose this is a phi, right? So can I write here the phi as, see, tan of phi, that is equivalent to, right, vertical component of the velocity, right, okay, by horizontal. Similarly, right, this will be the phi 1. So can I write it here? Tan of phi 1, that will be the vertical component of velocity by x. So how I can write down the formula of angle? That is v by vx, and that is equivalent to what? U sine of theta minus gt by u cos of theta, right, by u cos of theta, right? So this is how the velocity is changing with respect to time. Now, how these two equations, suppose I'm giving you all a very simple example because there might be the confusion for you all. See how we are going to calculate. Let us take an example. Particle is thrown at 30 meter per second at 30 degree. This is the trajectory of particle. At t is equal to 1 second, what will be the position of particle? Right, simple example I am taking, right, to explain in front of you all. See, r, something that is contributing in x plus something that is contributing in y, right? X, it is u cos of theta into t of I plus u sine of theta into t minus half gt square of j, right? So this will be 30 cos of 30 into I plus 30 sine of 30 minus phi of j. Right, okay, so this will be 30 cos 30, so it means that this will be 15 root 3 of I plus 15 minus phi of j. So what will be the position vector at that instant at t is equal to 1? The position vector will be phi root 3 of I plus, right, 10 of j. In x part, the particle has moved, right, to the distance of 15 root 3. In y part, particle has moved on to the distance of 10. This will be the position of the particle at t is equal to 1 second. This is the position of particle. Now what angle it is making, right? What angle it is making with respect to y? Tan of phi, that is ry by r of x. This is y by x. Is simple triangle we are having, na? Simple triangle we are having. This is phi, right? So this is 10, this is 15 root 3. Simple triangle we are having 10, 15 root 3. Phi 2s are, phi 3s are. It is 2 by 3 root 3. This is an angle that is making with respect to horizontal. What will be the velocity at 1 second? This is a position at 1 second. What will be the velocity? Something that is contributing towards x plus something that is contributing towards y. What it is contributing towards x, u cos theta, it is constant. What it is contributing towards y, u sin theta minus gt of j. So this will be 15 root 3 of I plus 15 minus 10. This is phi of j. This will be the velocity at any time instant. So at this point, the velocity can be defined like this way, right? Okay, see. This will be the velocity. This will be its horizontal component, 15 root 3. And this will be its vertical component, that is phi. Right? Now, what angle it is making with respect to horizontal, that is phi dash. So can I say tan of phi dash, that is equal to v of y by v of x, right? That is phi by 15 root 3. So that is 1 by 3 root 3. So that's why the position and velocity are right determined. I'll give you all one example in front. Right? Okay. Now, let's move back to the equation of time. Now see, when particle, see, suppose at t is equal to 0, the particle is thrown, at t is equal to 70, particle is hit. Right? Now rapidly we are going on to, right, to this some discussions. Right? So in that entire trajectory, what was the time of flight? So when it hits, the height of the particle is 0. It means Ry is 0. It means u sin theta, the vertical contribution, right, it will be equivalent to 0. The vertical displacement, this Ry part will be 0. So from this we are getting time of flight as 2u sin of theta by g. This is the formula of time of flight, right? This is the formula of time of flight. See how rapidly using the equation of position and velocity at time t, right? How rapidly we are going on to the, what will be the equation of trajectory, right? What is the vector? Position vector is u cos theta into time plus u sin theta of t minus half gt square, right, of j. The relation between y and x is trajectory, right? Relation between y and x, height and the horizontal distance. So what will be the y here? U sin of theta of t minus half gt square. What will be x here? U cos theta into t. Right, from this equation I am replacing, right, the value of the t as x by u cos of theta, right, into equation of y. So what I am getting, see, this is equation number 1, this is equation number 2, right? Okay, replacing 2 in 1, we got the equation of trajectory. What? That is x tan theta minus gx square whole divided by 2u square cos square theta. That is another equation of trajectory, that is x tan theta, right, 1 minus x by r, where r is a range. Okay, so we are having the two equations of trajectory in front. Okay, trajectory means that shows the relation between the horizontal contribution, right, the displacement of the horizontal contribution and the displacement of, not with respect to time. See here, there is a relation between y and x. Now something is like that, now relation between y and x, right? So time is not involved. Time is an intermediate quantity. Time is not involved. It is an intermediate quantity. So this is what the equation of the trajectory is. Range, easily. At t is equal to 0, particle is thrown with some speed u, right? At t is equal to time of flight 2u sin theta by g, it hits the ground. Now between these two time intervals, what is the distance, the horizontal distance covered? That will be obviously rx. Can I define it as a range? If t will be time of flight, right? So what is the range? Rx. u cos theta into t, the vertical component. We determine the vector na rx, right, of I plus ry of j, right. So what is the rx? That is range, right? U cos theta. Can I replace t as time of flight? 2u sin theta by g. So finally we are getting, right, the equation of range as u square sine of 2 theta by g. This is the range of the projectile. The maximum horizontal distance, right? The maximum horizontal distance, I'm writing it here. See how easily we are going on to the results. Okay, we have just seen, right, the velocity at any time, the position at any time, right, and trajectory, and then maximum. Now max height. Simple, very simple, right? Particle is initially thrown with some velocity. Horizontal component is u cos theta, this is u sin theta, right? Okay, now this will be the max height of the particle. For vertical contribution, right, we had this equation Rx, I'm sorry, R, that is equivalent to Rx of I plus Ry of j. Now at this point of projection, the vertical component of the velocity is u sin theta. At this, u sin theta is 0. So between these two intervals, between A and B, what is the maximum height covered? H max. So can I use the third equation of motion? Right? V square minus u square is equal to, right, 2g of h max. Right? Okay. Now g will be negative. Here final velocity will be 0 minus u will be u square sine square theta, negative of 2g h max, right? So from this third equation we are getting the equation of the h max as u square, I'm sorry for this stuff, right, is u square sine square theta by 2g. This is the equation of max height. How we are going to deal with the linear momentum? This has been asked in NEET examination. How we are going to deal with the linear momentum at time t, at any time t, right? Now you will like get a click, right? What kind of the stuff we are dealing with. What is the right magnitude of the linear momentum? It is mv. In vector form it is written as mv. So can I write momentum at any time t? That is mass into velocity vector. Now what is this velocity vector? That is contribution of x plus contribution of y, right? U cos of theta of I plus u sine of theta minus gt of j. This is the momentum at any time t. How easily we moved on to the momentum. Why this part was why that much easy? Because you are already aware about the, right, how velocity is defined. You all are aware of how velocity is defined. You all are aware of how velocity is defined. So that's why you can easily move on to the momentum. What is the formula of angular momentum? R cross P. Can I write R cross V? Angular momentum of a particle, and that angular momentum will be with respect to the reference point t is equal to 0. right, with respect to point of projection. To calculate the linear momentum, dot product is used. It's not a dot product, it's just a, right, a multiplication of a constant with a vector, right? To calculate the angular momentum, cross product we are going to use. Suppose let us take an example with C. If I'm talking about the linear momentum at t is equal to 0, linear momentum was P, right? Okay, the direction of the linear momentum is as same as of the velocity. Suppose at A point the linear momentum is PA. Suppose at B point the linear momentum is PB, right? Suppose at C point, right, the linear momentum is PC. Like this way the momentum is getting changed. But what about the angular momentum? It is a cross product, right? With respect to origin, this kind of the questions are always there in mains, advanced, okay, not in advanced but in mains and something like that. And this kind of questions are always there. Okay, how we can deal with the angular momentum, how we can deal with the linear momentum, how we can deal with the energies. Now, many students will be having a question in their mind, sir, we haven't dealt with the force till now. Then how we can directly move on to the linear momentum? Whenever the paper is coming in front of you in exam, na, right? Okay, they are decided, right, that you all are aware of all concepts, right? So that's why, right, we are having the mixed concepts kinds of thing, right, into the physics. We can define the linear momentum, right, for the projectile motion also. Slowly we are going to define the radius of curvature also, right, and we are going to define the, what we can say, lots of stuffs are there, energy also, kinetic energy, potential energy, lots of things are there. It shouldn't be the part of this, but if you want to move on from zero to hero, right, then this kind of the explanation of the projectile is must. Suppose at this point, what will be the value of the angular momentum A? What will be its direction? See, this is a cross product, right? Suppose, I'm just reminding you all, suppose if A cross B is C, then how resultant is to be found out? Using determinant. The same thing we are going to, if you need to calculate the value of L, we need cross product of R and V. The cross product of R and V multiplied with M, right, that will give you the linear angular momentum. So this is how. First of all, I'm writing the components of R, that is Rx, Ry. We are not having anything in Y, sorry, in Z, so it means 0, right? How we are defining this R, right? We've already seen, na? R, it is defined as Rx of I plus Ry of J. Similarly, Y, it is defined as Vx of I plus Vy of J. There is nothing in X. There is nothing in K. In Z direction, we are not having any kind of the motion parameter. So that's why I've written as 0. For velocity, I'm writing it as Vx, Vy, 0. Right? Okay. So finally, what will be the angular momentum of the particle? Right? Angular momentum, this will be M. Right? Okay. Rx, Vy minus Vx, Ry. This will be at any time instance t. For cross product, obviously, to calculate the resultant, we need to move on with the determinant only. Right? Now, what is the value of Rx? You all are aware of. See, what is Rx? U cos theta into t. What is the value of Ry? You are aware of U sin theta of t minus half gt square. What is the value of Vx? Right, that is U cos of theta is constant. What is value of Uy? That is U sin theta of, right, minus gt. This thing you all are aware of, right? If you all are aware of, see, again I am saying, right, if you all are aware of the velocity at time instant and the position and time instant, then and then the linear momentum, the angular momentum, right, this kind of the stuff will be quite easy for you all. And you, right, I'm damn sure that you are going to crack the question of JEE and NEET both. So this is how simple definition is there. mass into Rx Vy minus Vx into Ry. What will be the Rx, Vx, Vy? Sorry, this will be Vx. Again, I am writing clearly in front. Right? Rx Vy minus Ry Vx. Now what will be the value of Rx, Vx, Ry, Vy, all everything it is in front. You have to just replace, right, and replace that value in this stuff and get the angular momentum. Okay, what will be the direction K? Right, angular momentum. See, cross product of two vectors is always perpendicular to both. If I'm talking about A and B, so the cross product C is always perpendicular to A and B. Right, so you can see R we are having in I and J, right, velocity we are having in I and J, but angular momentum we are having into the third dimensions K. K is perpendicular to I also and K is perpendicular to the J. I, J, K are the unit vectors, right? So this is how the angular momentum is calculated. Energy. Kinetic energy at any time half mv square right. Can I take a magnitude of this velocity at any time instance? Can I take a magnitude of this to calculate the kinetic energy at any time instance? At any time instance between t is equal to 0 to the time of flight, right? See, so how we are going to discuss that stuff? See, it will be u cos of theta whole square plus u sine of theta minus gt whole square. I'm sorry, man. Right? Vector is u cos theta of I, u sine theta minus gt of j. Vector is like this way. I need to calculate the magnitude of this vector. See. So right now the student, those who have watched this lecture till now, right, they will be getting their answers. Why I moved on to the vector, why I explained this projectile, right, keeping the vector in front as the intermediate part. Why I first moved on to the position of the particle. Why I first moved on to the velocity of the particle. So this will be the velocity. This will be the kinetic energy at any time. Kinetic energy, this will be m by 2, right, under root of u cos theta whole square plus u sine of theta minus gt whole square. What will be the potential energy? Potential energy is always calculated with respect to the reference point. Okay, the ground is a reference point. At this point, what will be the potential energy with respect to time? Potential energy with respect to time, right, at any time t. What will be the height of the object and at any time t, right? So P is equal to mgh. H means r of y. So what will be the potential energy? That is mg, right, into u sine of theta into t minus half gt square. This is the variation of the potential energy. This is a variation of the kinetic energy, right, in between t is equal to 0 to t is equal to time of flight. What will be the mechanical energy or total energy? Mechanical energy is conserved. Let's move on to the total energy. Okay, the resultant of kinetic plus potential at every point. Okay, you can understand what kind of things we are seeing in this projectile, right? The last most important stuff, that is the radius of curvature. In this we are going to see even the concept of the centripetal, right? See, at t is equal to 0, particle is thrown. At t is equal to t, right, the particle hits the ground. Suppose I'm talking about the first point A, B, C, D. Now what actual the radius of curvature is? At any position, see, kindly mark my words, I'm highlighting it again, right? Okay, at any position on the trajectory of the particle, at any position on the trajectory of the particle, right, imaginary circle is drawn. The radius of this circle is curvature. At any instance of time, at any instance of a position, at any instance of a time, right, for a particle, at any position on the trajectory of a particle, one imaginative circle can be drawn, right? The radius of that circle is radius of curvature. Now, how we are going to identify that? Suppose this is velocity at any time instance t. Never see, J is in this downward direction, right? J is in downward direction, right? Okay. This will be the radius of curvature. We need to calculate this r, right? Suppose this is alpha, then this is alpha, right? Now, we need to calculate the radius of curvature. See, if I'm talking about an imaginary circular path, then there is always a presence of centripetal acceleration. There is always a presence of centripetal acceleration, right? So can I say this component of the acceleration as g cos of alpha, and it is providing the necessary centripetal acceleration to form this imaginative circle. Now we are having the stuff like this way. This is a circle. This is the component of g as g cos of alpha. It is providing necessary centripetal, right, so that particle can move on the circular path, and this imaginary circle can be formed. So what is the formula of centripetal acceleration? That is V by R. Can I say this R as a radius of curvature? Yes. Velocity at any time instance t by g cos of alpha. This is the formula of radius of curvature, right? Okay. Suppose, let us take an example. We are going to see this, right? I'm showing you an example in front. Okay. Okay. See, suppose particle is thrown at 30 meter per second, right? It is thrown with the 30 degree. What will be the radius of curvature at t is equal to 1 second? Right? In the previous slides, we have already seen this stuff. Okay, first of all, what is the formula of the radius of curvature? That is velocity at any time instance t, square of that whole divided by g cos of alpha, right? Okay, this alpha is angle made by velocity vector at time instance t. Right? So can I write it as R as u cos of theta, right? Okay, see, it is a square na, plus u sine of theta minus gt whole square, and square of this, right, whole divided by g cos of alpha. So what will be the radius of curvature? U cos theta, u square cos square theta plus u sine of theta minus gt whole square whole divided by g cos of alpha. Theta is this, alpha is at time instance the velocity that makes angle with respect to horizontal. There is a difference between theta and alpha. This is how the radius of curvature is calculated. Now suppose we are replacing this r, right, as 30. So 30 cos of 30. So it will be, right, 15 root 3 whole square plus, okay, 30 sine of 30, that is 15 minus 10. Okay, that will be phi of whole square by g cos of alpha, right? So this r will be 225 into 3 plus 25 whole divided by 10, right, into cos of alpha. Still we are not having the value of the alpha, because cos of alpha, that is equal to, right, velocity of y by velocity of x. What is y component of velocity? 5. What is x? 15 root 3, right? So this will be r is equal to 225, right, into 3, 225, 225, 225, right? So it's 15, 1, 6, 7, 675. It's 675 plus 25 whole divided by 10 cos alpha. Cos alpha is 5 whole divided by 15 root 3. Right, so r will be 70 whole divided by 5 into 15 root 3, right? 5 3s are, the radius of curvature will be 210 root 3 meter. This is how the radius of curvature is calculated. This is a phenomenon. Right, this is how the radius of curvature is calculated. Again, I am showing velocity at any time square g cos alpha, where alpha is angle that velocity vector makes with horizontal at that time instance, at that, this is at that time instance when the curvature is asked, right? So this is the formula of the radius of curvature. Now in this, the equation of velocity at any time t, you all are aware of this vector, that is vx of I plus vy of j. You can see how the concepts are interconnected with respect to each other. So this is what the projectile, the oblique projectile, is completely all about. Now immediately, right, we will move on to the concepts of the horizontal projectile motion. First of all, let's have the glimpse of it, right? See, okay, oblique projectile, right? First of all, I said it is a contribution of something in horizontal and vertical, right? Then I said moved on with the question solving approach, right? Then I moved on with the time of flight. Okay, first we moved on to the position and their angle, velocity and their angle. Then we moved on with the time of flight, right? Then we moved on immediately with the trajectory equation, two equations of trajectory. Then we moved on with the range, when with the maximum height, with the linear momentum, angular momentum, right? Energy, radius of curvature, right? Now we are going to see the sums of it, some of the PYQs of it. Let's move on to some of the important sums related to the oblique projectile motion, right? We have already seen, right? So all of those concepts we have seen. Now immediately we are going to solve all of those stuff. See, very simple. The velocity of a projectile at an initial point is this. Its velocity at the point B will be. Suppose the projectile is thrown with the initial velocity, right, vector, it is given as 2 of I plus 3 of j. It means its contribution into the x direction is 2 meter per second. Its contribution into the y direction is 3 meter per second, right? And the initial vector u is formed. At t is equal to 0, the particle is thrown. So this question is very simple, right? When it will hit, see here the air resistance is absent, right? So as due to absence of air resistance, right, air resistance is completely absent, and due to absence of it, right? There will be no change into the horizontal component of the velocity. And for the vertical component of the velocity also, we are having only one thing, that is acceleration. So in this case, what will happen? Suppose what will be, suppose let us take an example. Okay, with the velocity magnitude, right, he is projected, the same velocity magnitude it hits. Velocity magnitude, it is projected. The same velocity magnitude, right, it hits. Right? Same velocity magnitude it hits. Right? What will happen here? Right? What will happen here? Right? Suppose it is, see, the horizontal component is 2, so it means it is going to be constant. So this will be the horizontal component. But the problem is about the vertical component. Right? The problem is about the vertical component. The vertical component with respect to the initial point, it is going to change its direction. As I said before, projectile moves like this way. At the topmost position, the vertical component is 0, right? And after this, right, slowly, the vertical component is going to increase, and it is going to have the same value as it was having at the point of projection, but just the direction is reverse. So horizontal will be constant 2 of I, vertical will be negative 3 of j. So at point B, right, we are getting the answer as velocity at the point B will be 2 of I minus 3 of j, right? 2 of I minus 3 of j. Okay, A will be the perfect answer for this specific question. A will be the perfect answer for this specific. Okay, so it's very simple. Now let's move on to the second part. Two projectiles of same mass with the same velocity are thrown at an angle 60 degree and 30 degree with respect to horizontal. This question is asked into the IIT examination into the year of 2000. It is a kind of a special case of the oblique projectile motion. Okay, suppose this is ground, right? Okay, this is ground. Okay, suppose one projectile is thrown at theta, right? Another projectile is thrown at 90 minus theta. One projectile is thrown at theta, another projectile it is thrown at 90 minus theta. Suppose if this happens, both are projected with the same velocity. Both are projected with the same velocity. Now in this case, simple. Range. The formula of the range is u square sine 2 theta by g. Suppose for first I am replacing the theta, it is 2 theta by g. For second, right, suppose let us take an example, it will be 2 sine of 90 minus theta cos of, right, okay, 90 minus theta whole divided by g. So R2 again we are going to get it as sine of 2 theta by g. So suppose if this happens, we are getting the first result as range of both is same. Suppose if the two particles, one is projected at theta, second is projected at 90 minus theta, both are having the same velocities, then the range will be same. Both will hit the ground at the same point. What will be the ratio of time of flight? T1 will be 2u sine of theta by g. T2 that will be is equal to 2u sine of 90. It means cos of theta by g. So what will be the ratio of T1 by T2? That will be equivalent to 10 of theta. This is the important result I am right showing in front. And what will be the result, the ratio of their max height? That will be equivalent to 10 square theta. Right. Okay. So this is what the special case of the projectile motion is, what it states. Now see, 60 and 30. Suppose theta is equal to 30. What will be 90 minus 30? 60 degree. Right? It means this case, right, we need to follow. There, then which will remain same? Time of flight will remain same? No. its ratio is tan theta. Wrong. Range of projectile, yes, all of them wrong. Maximum height, its ratio is tan square theta. B is the perfect answer. In 2000 that has been asked. B is the perfect answer for this specific question, right? Let's move on to the next part. The speed of the projectile at the maximum height is half of its initial speed. The angle of projection is, this question has been asked in 2010. Speed at max height, it is u cos theta. Half of the initial speed, magnitude of the initial speed thrown at the angle of projection is u. So can I say u cos of theta, that is equal to half of the initial speed u. U is going to cancel. Cos theta will be half. Theta will be 60 degree and this 60 degree will be your angle of projection. A will be the perfect answer for this specific question, right? Let's move on to the next part. A particle is A is dropped from the height and another particle is projected in the horizontal direction. Situation states that this is a height h, one particle is dropped with initial velocity 0, second particle is thrown, right, with the initial velocity u 5 meter per second, the initial horizontal velocity. What will be the time difference when they will hit the ground? We need to select the correct statement among this. We need to select the correct statement among this, right? So this was the stuff. I'm moving aside. If you all need to pause the video and solve this question, you can do. I'm giving you all the 5 seconds, otherwise you're going to solve the question. So it's 5, 4, 3, 2, 1. First case is a case of motion under gravity. Suppose it is falling from the height. So we are having h is equal to half gt square. So t is equal to under root of 2h by g. In first case, right, time it will hit the ground, it is 2h by g. In second case also, it is a case of the horizontal projectile motion. And for horizontal projectile motion, we are about to see, right, but its time of flight is under root of 2h by g. So in both of the cases, right, okay, they both will not hit the ground at the same point, but they both will hit the ground at the same time because they are released simultaneously. Particle A will reach to the ground first, wrong. Particle B will be wrong. Both particles will reach simultaneously. C is the perfect answer with this, right? Okay. Next question. The maximum range of the gun of a horizontal terrain is 16 km. Maximum range is 16 km. G value is taken as 10 meter per second square. Then muzzle velocity of the shell is what? Okay, if I'm moving aside, if you want to solve this stuff, you can. I'm giving you all the 5 seconds. 5, 4, 3, 2, 1, 0. Rmax is equal to 16 km, right? See, whenever it is given maximum range, this word, it means what? Whenever it is given maximum range, it means what? The angle of projection is always 45 degree. This is one of the, what we can say, the theoretical statements of the oblique projectile. So it means that if I'm using the formula of range, max range, it is u square sine of 2 theta whole divided by g. So this will be u square by g. Maximum range, theta will be 45 degree. So it will be sine of 90. Sine of 90 is 1. So u square will be equivalent to gr. So u will be equivalent to 400 meter per second, replacing the value. C will be the perfect answer for this specific question, right? So this all are the easy sums, right? Okay, of this. Okay, this all are the easy sums, right, of the oblique projectile motion. Now let's move on to the next part, right? And that is another concept of horizontal projectile motion. Right? Are you all ready? Okay, let's move on. Okay, so students, till now we have seen the cases of oblique projectile motion and we have seen sums related to it. Now let's move on to the next most important concept, and that is the concept of the horizontal projectile motion. Right? See, if you are really able to understand the flow, right, of the oblique projectile motion, then it will be quite easy for you to understand this stuff. Right? It's very, very, very easy. What does the definition states? With respect to ground, right, from specific height, particle is thrown with some horizontal velocity u. Right? Okay, a simple definition, right, from height h, particle is thrown with horizontal velocity u. Then it follows a specific kind of a trajectory that is known as this kind of a motion performed by the particle, that is always the horizontal projectile motion. Now, what are the examples of horizontal projectile motion? Right? What are the examples of the horizontal projectile motion? The one visualization that is in front. The second example, right, bomb dropped from a plane. Bomb dropped from a plane. Suppose, let us take an example at the specific height with respect to ground. The plane is moving with the horizontal velocity like this way, right? Okay, simple example I'm giving and demonstrating in front of you all. The plane is moving with respect to ground. Let us take an example at the height of the 2 kilometer, right? Plane is moving like this way. Suddenly, right, it is moving with the horizontal velocity and suddenly drops the bomb, right? So the bomb follows this kind of the trajectory. Just follow my hand, right? Just follow my hand. Okay, the bomb is dropped, right? Okay, just follow my hand. The bomb is dropped. The bomb is following the specific kind of the trajectory, right? This trajectory is a a motion, the trajectory of a horizontal projectile motion, right? So there is one compulsion. Always horizontal velocity is there. There are some special cases in this also, but we are not moving to that much detail part, right? Okay, there are some special cases also. So this is what all about the horizontal projectile motion, right? Okay, same analysis is there, same question solving approach is there, right? Again, if I'm talking about the horizontal projectile, obviously it is a kind of the 2D motion. It means something that is contributing in horizontal part, plus something that is contributing in vertical part. The resultant of this two, it is giving the horizontal projectile motion. The same we saw into the concepts of oblique projectile. Something into horizontal, something into vertical. There is a slight difference between. There is a slight difference between the horizontal projectile motion and the concepts of oblique projectile. There is a slight difference between the projectile into the inclined plane, right, and the oblique projectile motion. There is a slight difference, right? If you are able to identify that difference, then this concepts would be quite easy for you all, right? Again, from height h, particle is thrown with the horizontal velocity u. It follows this trajectory, that is the horizontal, right? Okay, that is the this trajectory is of the horizontal projectile motion. Now, the most important stuff, you can see with respect to point of projection, with respect to point of projection, right? Particle is gaining some depth also and it is moving forward also. Suppose at t is equal to 0, the particle was projected at t is equal to t, time of flight it hits the ground. This is the first position of the particle. This is the second position, right? This is the second position, this is the third one, this is the fourth one, this is fifth one, right? So how to draw the position vector? This will be the position vectors, right? And this will be the final position vector with respect to ground. This is how the position of the particle is changing from the point of projection to the point where it hits. This is the, right, where the position of the particle changing from, right, to the initial to final position. Okay, initial to final position. Now, okay, see, you can see first horizontal distance was this much, right? After that it increased to this much. After that it increased to this much. After that it increased to this much, and finally it is reaching to the range of the projectile, right? With respect to point of projection, first height was this much. After that depth was this much. After that depth increased to this much part. Again depth increased to this much. Finally to this, and lastly it is reaching to H. You can analyze this situation in both of the cases, right? The displacement is Y also increasing, displacement in X is also increasing, right? Because in this case we need to identify the nature of the horizontal motion and the vertical motion. Again, right? Again, the air is absent. In this case also we are considering, right, air as absent, right? So horizontal, if air is absent, right, then we are not having any kind of the acceleration, right, okay, into the horizontal direction, right, that can increase or decrease this value of u. U is the horizontal velocity, na? Air is absent, right? So we are not having any kind of the, see, apart from the air, right, air provides a resistance. Apart from this air, we are not having any kind of this, right, stuff, not any kind of an external acceleration that can increase or decrease this velocity u of the particle. That can increase or decrease the velocity u of the particle. So it means the horizontal velocity of this motion, the horizontal part, the velocity that is contributing in horizontal part of this projectile is constant. If velocity is constant, then the motion is uniform. So the nature of the horizontal part, as we have seen right into the previous, it is a uniform, and vertically there is a presence of the acceleration g, right? So vertical will be uniformly accelerated motion. As you have seen into the oblique, horizontal was uniform, vertical is uniformly accelerated motion. The same analysis is for horizontal projectile motion. What will be the question solving approach? The question solving approach will be, yes, the same as we have seen into the oblique. This is a horizontal projectile. Thus, right, something that is contributed in horizontal part, that is I, plus something that is contributed into vertical part, that is J. Horizontal, that is uniform motion, right? Vertical, we are having the uniformly accelerated motion. It means all equations of the uniform motion are applicable. All equations of the motion parameters of uniformly accelerated motions are applicable, right? All, right? Position at any time t, the same procedure we are following that we saw. R, suppose initially this was a position vector, after that position vector changing onto this, then to this, and finally reaching to this position. See how the position vector is changing. See all of those vectors, right, we are considering with respect to point of projection only. Everything is with respect to point of projection, right? In another sense, t is equal to 0, right? There exist some cases, right, in which the t is equal to 0 is not the reference point, but in maximum number of the cases, right, we have taken this only. T is equal to 0, point of projection. How the position vector is changing with respect to time, right? And what angle it is making. See, suppose this is thrown with you. What angle it is making, right, with respect to horizontal. This is angle phi 1, right? Okay, this is angle phi 2, right? This is angle phi 3. This is angle phi 4. See how angle is changing with respect to time. Again, R, something that is contributed in horizontal plus something that is contributed in vertical. Horizontal is a uniform. What is the displacement of what will be the displacement into the y direction? Sorry, into the x direction if the motion is uniform. So can I write the equation of the displacement for the uniform motion? Right, see, velocity is displacement by time. So can I write it as displacement into velocity into time? So it means that displacement is x direction, that is velocity into the x direction in time. Particle was thrown with the initial velocity u and that was horizontal. It means that vertical component of the velocity is missing at the initial position. The vertical component of the velocity is missing. So we are writing down the equation. See, u of x into time plus I plus vertical motion is a uniformly accelerated motion. So I can write it as u of y of t minus half of gt square. If it is an oblique projectile motion, we replaced ux as u cos theta, ui as u sin theta. But this is a horizontal projectile. In oblique projectile, it was thrown at some theta angle with respect to horizontal. But in this horizontal projectile motion, it is thrown horizontally with respect to ground. So what will be the ux? U of t of I plus initial velocity component is 0. Why? Because it is thrown horizontally. No vertical component is present. In oblique projectile, we were having u sin theta into the initial position. But here we are having not. This will be minus half gt square of j. So what will be the equation of position with respect to time? Ut of I minus half gt square of j. This is how position of a particle is changing from t is equal to 0 to t is equal to time of flight. T is equal to 0 to t is equal to time of flight. Right? How the things are getting changed. But still one thing is remaining. How the angle is changing. Right? Suppose this is a position R1. This is a position R2. Right? R3. R4. How angle is changing? I am writing down the common formula. Tan of phi. Suppose if I am talking about this equation, see, suppose let us take an example. This is the horizontal projectile motion, right? I am talking about this position vector R, right? Can I say this is Ry, this is Rx, right? Okay, so this will be phi, right? This will be phi. So simple triangle tan of phi, that will be equivalent to Ry by Rx, that is equal to negative of half gt square whole divided by u of t. This thing is going to cancel. So tan of phi, the angle with respect to horizontal, with respect to horizontal, we are getting it as gt by 2u negative, right? gt by 2u. This is how we can define the position at any time t. Now, velocity at any time t. Obviously, yeah, it's very simple as we have seen in the oblique projectile motion. This is h. Initial velocity is u. Suppose this is the first position of the particle. Right? Now, velocity will be, see, horizontal component is constant here. Initial velocity, the vertical component of the velocity is 0, but after some time, right, g is acting in downward direction. So from 0, right, g is increasing this vertical component in downward direction. Initially it is 0, it doesn't mean that for entire motion it will be 0. Why? In vertical direction there is a presence of acceleration and it is going to increase the vertical component of velocity. So right now we are having Vy, this is x. Here we are having only horizontal component now. So here the velocity is changing like this way. It is like this way. See, slowly, 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 slowly. See, my thumb is rising. See, now my thumb is absent. See now, slowly, 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 my thumb is rising into the downward direction. Like this way, the velocity of the y component of the velocity is getting changed. Same concept, velocity vector, that is equal to Vx of I plus Vy of j. Right? What will be x? U of x of I, because horizontal is uniform, vertical is u of y minus gt of j. So what will be the velocity? That will be horizontal is u initial, right, minus gt of j, right? So this will be the right velocity at any time instance t, right, at any time instance t. Velocity at any time instance t. Right? But how the angle? See, there is one angle with respect to horizontal, na, phi. Right? So angle with respect to horizontal will be tan phi. Right? Okay, this will be with respect to horizontal. That will be Vy by Vx, right? So that is equal to minus Gt by U, right? So what will be the tan phi value? I'm writing it here. The tan phi is equal to negative of Gt by U. This is what the velocity, right, vector is making angle with respect to horizontal axis. So this, see, there is a slight difference. In that we were having U cos theta of I plus U sin theta minus gt of j. Here initially the y component is absent, so we are having only the horizontal u of I minus gt. This will be 0. Right? Obviously trajectory is a relation between y and x, right? So directly we are going to take this equation, right? Ut minus half gt square, like this way, right? Okay. So ut of I minus half gt square of j. What will be the value of x? U of t. What will be the value of y? Negative of half gt square. Can I replace t as x by u, right, in this equation? Right, so I'm getting the equation of trajectory as, right, y is equal to, I'm sorry, simple thing, it is in front, it's very simple. Y is equal to negative of half, right, of g, that is x square by u square. So this is the equation of trajectory, gx square negative by 2u square. Trajectory, as we have already seen, it shows the relation between y and x. Right? So this is what the equation of trajectory. Trajectory, it means that the equation of a curve that particle is following, right? Okay, that is the equation of trajectory. Okay, range. Before moving on to the range, first of all, let's move on to the time of flight, right? Suppose at t is equal to 0, right, particle is thrown with the horizontal velocity u, right? When it hits to the ground, time is t, right? If I'm talking about the vertical motion, see, rx of I plus ry of j. If I'm talking about this ry part, right, can I say r of y, that is equal to, right, u of y of t minus half gt square of j. Why I taken g as a negative? Because g is acting into the downward direction, right? Okay, so that's why I've taken, right, g as negative, because it is in negative j part, right? Now, between this t is equal to 0 to time of flight, how much amount of the vertical displacement we are having? Negative of h. Because with respect to point of projection, h is in downward direction. The particle is covering a depth, not height. If it would be height, then it would be positive with respect to point of projection. But with respect to it, it is covering some depth. That's why we are taking this as negative. Vertical component of velocity is 0. Initial vertical component of the velocity is 0, is negative half gt square of j. So here it comes time of flight as 2h by g. Right, 2h by g. Now, particles takes under root of 2h by g, right, to reach from this position to this position. Then what would be, see, the maximum vertical distance covered is h. What will be the maximum, like not maximum, what will be the horizontal distance covered? Obviously, again, we are going to same, right, rx of I plus, right, ry of j. Now we are going to take this horizontal part. Okay, so rx, that is equal to range, that is equal to u into t. So range, that will be u, this will be time of flight, and that will be under root of 2h by g, right? Okay, so this will be the range of the horizontal projectile motion, r, the horizontal distance covered, right, between the point of projection and time and the point of a destination. Okay, now the maximum height, obviously it will be negative h with respect to point of projection. Okay, so this was all about the horizontal projectile motion. There is a small difference, just it is thrown with the horizontal velocity u. It is thrown with the horizontal velocity u. Now let's move on to some of the important, see, we are having the most important formulas in front, right? Okay, I'm showing you all. Okay, first equation of trajectory is minus gx square by 2u square. Position u of I, right, minus half gt square of j. Velocity, sorry, ut of I, u of I minus gt of j. Time of flight under root of 2h by g. Range u under root of 2h by j. These are only the formulas for the horizontal projectile motion, right? The useful formulas for that. If you want to take a snap, I'm giving you all of 5 seconds. You can have a snap of it. It's 5, 4, 3, 2, 1. So students, those who are watching, like those who have watched the lecture till now, right, they might be get bored into the initial part of this session. Sir, you are consuming, they might be having the question into your mind that, sir, you are consuming a lots of time in explaining the position into the oblique projectile motion, in explaining the velocity in oblique projectile motion. We build the foundation of a concept at that point of time. And right now, see, in within 10 to 15 minutes, right, we have completed, right, we have completed all of those formulas. See, you can have the glimpse, all of those formulas, what is a horizontal projectile, because this stuff you have already seen. What is the nature horizontal, what is the nature of vertical? There is a small difference. In oblique, there was a vertical initial velocity, there was an initial velocity component into the vertical direction, but here we are having only the horizontal component, and that is also u, not u cos theta. Because u cos theta, theta is 0, cos 0 is 1, that's why here it is, we are having u, right? U cos theta, theta is 0, so it is u cos of 0, right? So that's why it is 1, and that is equivalent to u, right? After that, we immediately saw, right, the question solving approach the same way. So that's why we build up the foundation at that point of time, and that is very helpful right now. Okay, time of flight we saw, position at any time, the angle, the velocity at any time, that respective angles, right? Okay, the maximum height, it's okay, it's not a big deal. Okay, now let's move on to the questions of the horizontal projectile motion. So students, right, we have already seen to the concepts of the horizontal projectile motion. Now let's move on to some of the important sums related to it. Okay. A stone is just released from the window of the train moving along the horizontal straight track. The stone will hit the ground following the path. This is an horizontal track, right? Train is moving on the horizontal track. What is the question states, right? This is a horizontal track. The train, right, it is moving, okay, on the horizontal track, okay, with the velocity v. Let us take an example. The horizontal component, right, of the velocity of the train is v and the vertical component is 0. Now suppose, right, what it has been dropped, a stone is released. See, the velocity of the train is constant. It means that acceleration into the x direction is 0. If stone is inside the train, it means the whatever the amount of the velocity train is gaining, the same amount of the velocity stone has. So when it is released, already it is having the horizontal velocity, and due to the acceleration, right, gravitational acceleration of the earth, slowly, initially, right, the vertical component of the velocity is 0, but there is a presence of the gravitational acceleration, so slowly, right, it will, right, have the vertical component of the velocity as v, right? So it is having one horizontal component of the velocity. Slowly g will gain its vertical component. It means it is having both component. While it hits the ground, it is having the both component. While it was projected, it was having only one horizontal component. So it means it will follow this kind of the trajectory, and it will be the case of the horizontal projectile motion. And in that case, the trajectory will be parabola. C will be the perfect answer for this specific question. C will be the perfect answer for this specific question, right? A bullet is dropped from the same height when another bullet is fired. The same question we saw, right, into the case of the oblique projectile motion, and the thing is repeated here, right? One bullet is dropped and second bullet is fired with the u meter per second. The bullet that is dropped from the height h, it is having the time period t is equal to 2h by g. And second, that has been fired horizontally, it follows the, right, trajectory of the horizontal projectile motion. The trajectory of the horizontal projectile motion. For that also, the time is under root of 2gh. Both will not hit the ground at the same point. Both will hit the ground at same time. Again, I am repeating, kindly highlight all of those words. Both will not hit the ground at same time. Sorry, both will not hit the ground at the same point. They will hit the ground at same time. Right? Okay. So in this case, right, they will hit the ground simultaneously, and this is the perfect answer for this specific question. Right? Next part. Aeroplane is flying at a constant horizontal velocity of 600 km per hour at an elevation of 6 km. At the height of 6 km, right, it is moving with the horizontal velocity of 600 km, right, per hour. Now it releases the bomb, so it can target it at the earth. It releases the bomb, then obviously if it is going to release the bomb, then it will follow this kind of trajectory, right? It will follow this kind of trajectory, right? Then obviously, if I'm talking about a pilot who is inside, right? See, it is following the parabolic trajectory for a person who is on ground, right? So for a person who is actually on the ground, right, when the bomb is released, initially it was having the horizontal velocity that is 600 km per hour, but due to the presence of the acceleration, gravitational acceleration into the downward direction, right, it will gain, initially the vertical component of the velocity is 0, horizontal is 600 km per hour. Slowly, g will increase the vertical component of the velocity, and it will follow the trajectory like this way, right? It will follow the trajectory like this way, right? So let's see the correct option on parabolic. No, if pilot is saying, then bomb is dropped like this way, because pilot is also having the horizontal velocity. When the bomb is dropped, it is also having the horizontal velocity. So if pilot is an observer, then the relative horizontal component, right, will be 0. So only vertical effect will be there. So with respect to the pilot inside the plane, bomb is leaving like this way. But with respect to observer on the ground, bomb is coming like this way. Right? So on a parabolic path is seen by the observer on the ground near the target. Right? Observer is here. Okay, this will be the target. Okay. A bomb is dropped from an aeroplane. Suppose. See, direct formula based questions are always coming. This is a kind of the, what we can say, the theoretical and the conceptual based question. Suppose if air resistance is taken into the consideration and bomb is dropped from an aeroplane. Generally, in all cases of the projectile, what I told you before, right, we are not taking any kind of the air resistance into the consideration. But suppose if we are taking it into the consideration. Right, it is thrown. Suppose if air resistance is absent, right, then it will follow, it was thrown into the with the horizontal velocity u from the height h, right. So this was the hitting point if air resistance is absent, right, no air resistance. No air resistance. Now suppose if air drag is there, what will happen? This air drag will always resist the motion, right? So velocity, horizontal velocity is in this direction. This will be the air drag. So it is opposing the motion. So obviously it is going to decrease the horizontal component of velocity. Vertical component is not affected because height is quite more. H is more, right? So vertical component is not going to affect, and if it is going to affect, then like negligible effect is there. Air resistance is absent, and obviously this thing is going to follow. And suppose if air drag is there, then obviously it is going to drag particle into the opposite direction of the motion. It is going to, right, the acceleration that is produced by air drag, it is going to oppose the velocity. So in that case, right, trajectory will be like this way. Range will be less as compared to the previous one in which air was absent, right? So this was our hitting target, but in the absence of the air resistance. But when air resistance is present, it will hit just nearer to the hitting point. So it will, so at that point, right, see, plane will be here, right? So this is an exact point, okay, below the plane. So in absence of air resistance, right, when it will hit the bomb will hit the target, plane will be exactly above it. But in presence of air resistance, when it will hit the ground, right, plane will be ahead of the bomb. So if he falls exactly in presence of air resistance, no. Yes, it will fall behind the aeroplane, and this is the perfect answer for this specific question. Right, that's the perfect answer for this specific question, right? So this one is a homework from my side. You can do it by your own, and answer of this question you can just write a mention into the book, sorry, into the beneath the video into the comments, right, beneath the video into the comments. Okay, so this was all of the cases of the horizontal projectile motion. Now let's move on, right, to the another concept of third classification of the projectile motion, that is motion, inclined main projectile motion on an inclined plane, right? So let's move on to that. So let's move on to, we have seen the concepts of oblique projectile, then we moved on to the concepts, the sums of it, PYQs related to it, then we moved on to the concepts of the horizontal projectile motion. Now this is the third type of the projectile, that is inclined plane projectile motion. Now, okay, as usual, there was a slight difference between oblique and horizontal, right? Even this is also the same situation. There is a slight difference between the, right, inclined plane and oblique. Now what is that difference? right? Okay, see in oblique, okay, see first of all I want to show you all a difference. If I'm talking about a oblique projectile, horizontal projectile, and inclined plane, right? If I'm talking about the difference between these three, right? If I'm talking about the difference between these three, this is inclined plane projectile. Okay, in oblique, horizontal motion was uniform, contributing u cos theta. Vertical motion was uniformly accelerated motion. The component of the velocity that was contributing was a u sin theta, right? In horizontal projectile, the horizontal motion was uniform, right? And contributing velocity was v. Vertical motion was uniformly accelerated. Vertical initial velocity was 0, right? In both of the cases, right? In all of those cases, air was absent. But now, in the inclined plane, like inclined plane projectile motion, again we are having the two type of motion, horizontal and vertical. Horizontal will be uniformly accelerated. Vertical will be uniformly accelerated. Uniformly accelerated, contributing towards each other, right? And creating a resultant to obtain a projectile. Horizontal uniform, vertical uniformly accelerated. Here both are uniformly accelerated. There is a small difference between inclined plane and, right? So rapidly we are going to see this thing. Okay, so this was an actual difference. Now see, inclined plane projectile. What's an actual scenario for that? See, the plane that is inclined at some angle with respect to ground, that is alpha. Plane that is inclined at some angle alpha with respect to ground, right? Now suppose this is an inclined plane at an alpha. Particle is thrown with speed u, making angle beta with respect to, okay, see, plane is inclined at what angle? Alpha angle with respect to horizontal. Plane is inclined at alpha angle with respect to horizontal. The second part, object is thrown with speed u and at an angle beta with respect to inclined plane. If you really want to understand the concept of the inclined plane projectile motion into the most convenient way, then you have to always assume the inclined plane as an x-axis, perpendicular to it as a y-axis. Always assume this. Inclined plane as x-axis. This is the inclined plane, right? Okay. This is always assume inclined plane as the x-axis, perpendicular to it as a y-axis. It means this will be the x-axis, right? And perpendicular it is a y-axis. Now, it means whatever we are going to analyze here right now, right? The observer will be on inclined plane. This is an observer, because the motion without an observer is not an possibility, right? Okay, motion without an observer is not an possibility. So whatever we are observing now, right now, okay, it will be with respect to inclined plane. The observer is not on the ground, the observer is on the inclined plane. Right? Now, with respect to the inclined plane, we are having the two components. One that is a horizontal component u cos beta. Second, that is a vertical component u sine of beta. U cos of beta, u sine of beta. U cos of beta, u sine of beta. Right? Okay. U cos of beta like this way. I'm sorry, this is not exactly perpendicular. We need to draw the perpendicular. Okay, like this way. This will be u sine beta. Right? So as usual, what will be our analysis? Something that is contributing into the horizontal, something that is contributing into the vertical. Resultant of this, this is a projectile. Like this. Right? This is the projectile and its respective trajectory. Right? Okay, now see. What is the actual difference between all of this type of the projectile and the main difference? G is acting downward direction, and with respect to the inclined plane, we are having the two components of G. This will be G sine alpha. This will be G cos alpha. Everything is going on with respect to the inclined plane. Two components of the G are there. This is G that is acting into the downward direction, right? Why the horizontal of the inclined plane projectile motion is uniformly accelerated? Why the vertical motion of the inclined plane projectile is uniformly accelerated? Because here G is making two components with respect to the inclined plane if the observer is on inclined plane. It means that, very simple thing, if I am having u sine of beta, to increase or decrease, I am having G cos of alpha. This is the vertical part. If I am having u cos of beta, again u cos of beta, I am having G sine of alpha. Right? This is the horizontal part. This is the nature of the horizontal motion, right? And this is the nature of the vertical motion. Right? See, for horizontal motion, the velocity that is contributing in horizontal motion u cos beta, it is having one acceleration. In previous cases, right, for the horizontal component of the velocity, we were having no acceleration because external acceleration was also zero and air was also absent. But in this case, against u cos beta, we are having the acceleration value, that is G sine alpha. Even that is also constant. And against the vertical, this is all, everything is going on with respect to inclined plane, right? Everything that is going on with respect to the inclined plane, right? With respect to inclined plane. Right? Everything is going on with respect to the inclined plane. Right? So, for the vertical component of the velocity, there is an acceleration, it is also constant. With respect to the inclined plane on x-axis, we are having acceleration. Even on the y-axis, we are having the acceleration. So, for that reason, in inclined plane projectile, right, we are having the two. The horizontal motion, that is I, plus vertical motion, right, that is J. The horizontal motion is the uniformly accelerated, vertical motion is the uniformly accelerated. It means that in horizontal, all the equations of the acceleration constant we can apply in this. All the equations, right, of constant acceleration, right, we can apply in this. In this, like both of this, but both of the contributions are uniformly accelerated. This is what actual concept states. The actual thing in front, right? If you want to take a snap, this is a black screen. I'm just giving you all the 5 seconds. 5, 4, 3, 2, 1. That's it. Right? Analysis, what it states. See, I'm drawing it here. This is alpha. This is thrown u with respect to beta. This is G, right? G is having the two component. One, G sine of alpha, G cos of alpha, right? The second one, components of velocity, u sine of beta, u cos of beta. So what does the analysis states? That the nature of the horizontal motion of an inclined plane is uniformly accelerated motion. The nature of the vertical motion, right, of an projectile motion on an inclined plane is uniformly accelerated motion, both. This is our final analysis. Similarly, in this we are having only two equations, right? Not more than that, right? Okay. So, question solving approach. What will be the position? Rx of I plus Ry of J, right? Horizontal contribution uniformly accelerated, vertical contribution uniformly accelerated. What was the equation of the displacement in uniformly accelerated motion? Rx u cos of beta of t minus half g sine of alpha t square. This is its horizontal contribution. S is equal to ut plus half at square I have used. For x, u I have replaced with u cos beta. Why? Because with respect to inclined plane, the horizontal component of velocity is u cos beta. For vertical contribution, we are having u sine of beta minus half g cos of alpha t square j. Why I have taken g sine alpha as negative, g cos alpha as negative? See, both are trying to oppose the velocity. Here g sine alpha is against the u cos beta. Here g cos alpha is against the u sine beta. Both are opposing the initial velocity vectors. That's why, right? And even according to the sign conventions. Now, how we can able to identify the sign conventions will be like this way. This will be negative j, right? This will be positive j, right? This will be negative I, right? And this will be the positive I, right? Time of flight. Here, what will be the equation of C? This is position at any time t. Now, what will be the equation of velocity? Simple. V, that is something contributing towards x, plus something that is contributing towards y. Right? Okay, that is something contributing towards y. Now, the x horizontal motion is uniformly accelerated, vertical is uniformly accelerated. So, can I write u cos of beta minus g sine of alpha into t? This is the change in velocity into the horizontal direction with respect to inclined plane, plus, right, u sine of beta, right, minus g cos of alpha into t. Angles of everything with respect to inclined plane, the same procedure we need to follow that we did into the previous part of this lecture, right? So this is velocity with respect to time t. Time of flight. So whenever with respect to inclined plane, whenever it is hitting this, right, can I say Ry is 0? The height with respect to inclined plane, whenever the particle is hitting, the destination is 0. T is equal to 0, particle is projected with u, angle beta, inclined plane angle alpha. T is equal to time t, it is hitting the ground. From t is equal to 0 to time t, right, when it hits the ground, with respect to inclined plane, the height is 0. Can I take this y component as 0? U sine of beta of t minus half g cos of alpha into t square as 0. Here t will be time of flight. 2u sine of beta whole divided by g cos of alpha. This will be the time of flight of the projectile, right? Inclined plane projectile motion. The most important equations are 4 only. The first, see, it is very simple, basic concept. If you are having this, right, relation between y and x, you can obtain the equation of trajectory. but that is not much needed, but you can obtain. We obtain the equation of flight, time of flight. Now, if we are replacing, see, what was the Rx? U cos of beta of t minus half of g sine of alpha into t square. If t will be time of flight, then Rx will be range. So range will be u cos of beta, right, into time of flight, 2u sine of alpha beta whole divided by g cos of alpha minus half g sine of alpha, right, 2u sine of beta whole divided by g cos of alpha whole square. A very long equation of the range, but we are not interested in this equation, but yes, we are aware of the concept. What? We need to replace the equation of time of flight into the horizontal part to get the maximum range, right? To get the maximum range of the projectile like this way. Okay. So the four most equations are important, right? R, equation of R, equation of V, time of flight and range, right? Range is also having some equation, right? But this much is enough for you all, right? So this was nothing else but just a case of the horizontal projectile motion, right? The case of horizontal, not horizontal, the case of inclined plane projectile motion, right? So here the projectile motion ends. Now we will move on to its sums, right? And then to the circular motion and relative motion, Riemann and Riemann problems. Okay, so now let's move on to the sums of those. So we have seen the concepts of the horizontal projectile, inclined plane projectile motion. Now let's move on to, okay, see, we are going to see two sums. One I'm going to show in front of you, and second I'm going to give you all a homework. Because inclined plane projectile is having the two kind of the phases. First, where it is thrown from top to bottom and from bottom to top, right? So this is the calculate, only two, as I said before, here only two type of the, right, 2-3 formulas are there, not more than that. Suppose, find the range of the projectile of the inclined plane which is projected perpendicular to the inclined plane. If you need to solve the sums of the inclined plane into the very convenient manner, then I told you all, right, consider the x-axis, the inclined plane as x-axis and perpendicular to it as a y-axis. Inclined plane as an x-axis and perpendicular to it as a y-axis. Now, first of all, this is your alpha, beta will be 90 degree. What we need to calculate? We need to calculate the range, right? So first of all, we are going to calculate the time of flight and we are going to apply it direct, 2u sine beta whole divided by g cos of alpha. What is the value of beta? 90 degree. Velocity thrown, that is 20 into sine of 90 whole divided by 10 cos alpha, that is cos of 37. Cos of 37 is 4 by 5. So here we are getting time of flight as 5 seconds. So from t is equal to 0, it has been projected. It will hit the ground after 5 seconds. It will hit the ground after 5 seconds. Now, what will be the range? As I said before, we have to use this formula of the range. U cos beta of t minus half g sine alpha t square. But this will be quite easy because we have already calculated the time of flight, right? Okay, so range, this will be u cos of beta of t minus half g sine of alpha into t square, right? So u cos beta, beta is 90 degree, right? So u cos of 90 into 5 minus 5 into sine of 37 into 25. R will be negative because with respect to point of projection, R is in downward direction, right? So here we are getting the range as 75 meter. Okay, so B is the perfect answer for this specific question, right? So this is the question regarding the range of the horizontal projectile motion. This question is a kind of a homework from my side, right? Kindly do it. Kindly do it. Okay, homework from my side. Okay, so now let's move forward. Kindly, I will be waiting for your answers, right, for this question beneath the video, and I want you all to try this, right? This is a question of projectile on the inclined plane. Okay, now after this, okay, so let's move on to the next concept of the circular motion. Okay, so we successfully did the sums of the inclined plane projectile motion. It's okay, we were okay, those were quite less, but it's not a big deal. Now the next part of the motion into the 2 days, circular motion, right? What actual the circular motion is, right? What are those relevant concepts? Okay, the classification of the circular motion, okay, into the uniform circular motion and to the non-uniform circular motion, the main aspects of the acceleration, right? All of those important stuffs we are going to discuss within the short period of time. So are you all ready? Successfully we have completed the almost, right? Okay, the very awesome concept of this chapter. Now, okay, circular motion, right? If you have heard about the song Ghumar 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 Re Ghumar Ghumar Ghumar. Now, what is a circular motion, right? Okay, have you ever what do you say, roll that kitchen into your finger like this way? Have you ever moved on to the this one, the kingdom, that Asal World or the Imagica kind of a theme parks, right? Have you ever visited any kind of the roller coaster ride? Have you ever visited, right? Okay, a giant wheel. Have you ever taken, have an experienced, right? Did you ever have an experience of this giant wheel? Many students have, right, have experienced that part. Okay, I must say it is nothing else but the kind of the circular motion. Have you ever taken joy, okay, having a ride of a train that is moving onto the circular path into the theme parks, right? Have you ever? That is one of the examples of the circular motion. Now, what it states, circular motion is a movement of an object along the circumference of the circle. Movement of an object along the circumference of the circle. Why? Are we having any kind of another alternative, or are we having any alternative for that? Why particle is only moving on to the circumference of the circle? Why? There are lots of paths are there, lots of paths are there in this universe. There is a curvilinear path, there is a rectilinear path, there is a path for a periodic motion, there is a path for to and fro, lots of paths are there. Why that particle is only performing, right? It is moving on to the circumference of the circle. Why? Is there any kind of a responsible thing for that? Is there any kind of the responsible thing for that? Is there any kind of the responsible factor for that? Is there any kind of the responsible physical quantity for that? Yes, centripetal force and acceleration related to it, that is named as centripetal acceleration. Why? Why it is named as centripetal acceleration? Why the force is named as centripetal force? And what is the reason behind that? That force, that relevant acceleration is forcing the particle to move on the circular path. Why? Lots of questions arises into the mind, right? We will answer them one by one. So, the basic definition of the circular motion is what? The motion of a particle around, or you can say the motion of the particle on the circumference of the circle. The motion of a particle on the circumference of the circle, that is the circular motion. Circumference of the circle, that is circular motion, and the responsible thing is a centripetal force behind it. Why it is known as centripetal force? For a moving particle on a circular path, right, it always acts towards the center. it always acts towards the center. Always it acts towards the center. So for that reason, this is known as centripetal, towards the center. Suppose this is a particle, let us take an example, it is moving on from point A to point B. Right? Point A to point B. Okay? So, the angular displacement of the particle is pi by 2. Angular displacement of the particle is pi by 2. But how many types of forces are acting in this on this specific particle? First, the centripetal force is acting. Second, centrifugal force is also acting. Array, sir, we are confused in centripetal and now we introduce another kind of the force, that is a centrifugal. What the hell, right? You are having what we can say a scenario in your mind that you want to completely dip the students in physics. Okay, what is a centrifugal? Whenever the particle is moving into the circular path, now one force, right? Okay, that is responsible, that forces the particle, right, to follow that path. That is centripetal. But while following that path, right, one outward force that particle exerts, that is centripetal. It is against this centripetal force, that is centrifugal. All of the time, it is not necessary. Suppose a particle is moving onto the circular path, one centripetal force is acting towards the right center. Same, one particle, this particle is exerting the force outwards, that is known as centrifugal, right? Okay, suppose if I'm moving onto the circular path like this way, right? Okay, if I'm moving onto the circular path like this way, right? I am exerting one force that is outward. Okay, okay, suppose, see, very simple, like this way. Merry-go-round, it is moving like this way. So one force that forces a particle to move on the circular path, that is a centripetal, and it is acting towards the center. But another force that particle exerts outside, right, that is a centrifugal against the centripetal. It is not necessary that all the time this fugal and centripetal, they are going to cancel the effect of each other. No, it is not necessary. It completely depends on, right, what kind of the activity that is going on. Okay, so now, so this is what actual, the explanation of the circular motion. Now, what it is a classification? Basically, we are having the two kind of the circular motion. The first one, that is a uniform circular motion. The second one, that is a non-uniform circular motion, right? Uniform circular motion, motion of a car along the straight road, on the circular path. Have you ever, have you ever, death well? Have you ever noticed, right? It is moving. The death well is like this way, right? Okay, this is the ground, right? Particle is moving on this circle of this radius r. But its speed is uniform, right? And it is nothing else but the uniform circular motion. The motion of an electron around the nuclei, the motion of a planets around the sun, the motion of the satellites around the earth, right? The motion, the revolution of the earth, all of these things are the examples of the uniform circular motion. Practically, their paths are they're elliptical, but theoretically, for ease of a calculation, right? For ease of a calculation, right? We are taking it as a circular. So these all are the examples, right? Now, what is an actual difference between the uniform circular motion, non-uniform circular motion? What kind of the parameters are involved in both, right? So first of all, I want to move on to the some of the important definitions, those who are involved into the circular motion, right? Okay, generally into the circular motion. All of those important terms, those who are involved into the circular motion, and then we will move forward to the uniform circular and non. So some important terms. Some important terms. Let us take a very simple example. If I'm taking a desk, right, it is rotating like this way, right? First, angular displacement. The first most important term is angular displacement. Let us take an example. If the particle is placed at this position A, right? If particle is placed at this position A and after some time it is reaching to point B, right? Point B. Particle is starting from t is equal to 0. It is starting from point A and it is reaching to the point B. What is a displacement? What is this angular displacement? If I'm talking about an analogy, what was the displacement? Right? What was the displacement? If I'm talking about the rectilinear motion, right? If I'm talking about the rectilinear motion, what was the displacement? The same analogy we are going to use for the angular displacement. The same analogy we are going to use for the angular displacement. So it is a point, it is an angle, sorry, not a point, angle, right? Angular displacement, right? It is an angle, right? That is made by a point that is moving onto the circular path, right? Angle made by a point, right? Or a particle, right? Point, or in another sense, point like mass, that is particle on circular path between 2 points of a motion, between 2 points of motion, right? That is its angular displacement. Here the theta is an angular displacement. Now what is an angular velocity? The change in displacement with respect to time. Sorry, change in position, angular displacement, right? Or you can say angular displacement with respect to time, that shows the amount of the angular velocity, with what angular velocity the particle is rotating. Sorry, the displacement, angular displacement with respect to time, that is another factor, then another important term. What is angular acceleration? Delta omega by delta t is your angular acceleration, but here we are having two types of acceleration in the circular motion. Okay, the first one, that is a centripetal acceleration, right? The centripetal acceleration, that is acting towards the right center and that is enforcing the particle, right, to move on the circular path. That forces the particle to move on the circular path. One another, see, centripetal acceleration is Fc, force is mv square by r, right, and acceleration is v square by r, right? Okay, x towards the center and responsible thing for particle to move on circular path. There is another type of acceleration, that is known as, see, this is a centripetal acceleration, that another one is a tangential acceleration, right? This tangential acceleration always acts, right, on a tangent to the path. Suppose this is a velocity, right? So this will be the direction of tangential acceleration, or this will be the direction of the tangential acceleration. It is either going to increase the velocity or either it is going to decrease the velocity, because it is always acting towards the, like, it is, see, if you are drawing a tangent, right, onto the circular path, that shows the directions of the velocity, right? Same is for the tangential acceleration. Either it is going to increase the velocity or either it is going to decrease the velocity. So for that reason, this tangential acceleration, it is defined as dv by dt. There is another term, it is known as net acceleration. Basically, if a particle is moving onto the circular path, there is always two types of acceleration. The first one is a centripetal and second one, it is a tangential, right? I'm not talking about any kind of the classification, whether it is a uniform motion or non-uniform circular motion, no. But generally, right, if the particle is moving onto the circular path, then always it is having the two kind of the acceleration. The first one, that is a tangential acceleration. The second one, that is a centripetal acceleration. So the net acceleration is resultant of both, right? So that will be, okay, that is v square by r, right, whole square plus dv by dt, right, whole square. Okay. Apart from this, if I'm talking about the motion parameters, what is the radius vector, you all are aware of. What is the velocity, you all are aware of. What is an acceleration, you all are aware of, right? So these are some of the important terms related to the to the circular motion. Guys, if you want to take a snap of it, you can. Right now we are moving forward, right, to the classification of uniform circular motion. 5, 4, 3, 2, 1, that's it. The motion of the particle in merry-go-round, right? The motion of an electron round the nuclei, right? The motion, the revolution of the earth, the motion of a satellite along the earth, the motion of the planet, right? Those are all, right? The motion of a second end of the clock, the motion of an hour end of the clock, right? The motion of the minute end of the clock. It is the uniform circular motion. Why they are known as a uniform circular motion? Because let us take an example. What was the general definition? Right, whenever the particle is moving onto the circular path, right, there are two types of accelerations acting on it. One that is a centripetal and second one that is a tangential. If the tangential acceleration on the particle is going to be 0, if the tangential acceleration of the particle is going to be 0, then what will happen? Here on the tangent we were having the velocity. So in the direction of velocity or into the opposite direction of the velocity, there is a no, what we can say, the acceleration is, what we can say, absent. Okay. So there is no acceleration to increase or decrease the velocity of a particle on the circular path. First point. Second, there is no acceleration that can increase or decrease the of particle. So it means that what will happen? The magnitude of the velocity is constant. Magnitude of the velocity is constant. Direction changes. It means speed is constant, because speed is a scalar quantity, right, and velocity is a vector quantity. And for a vector quantity, right, if you want to define the vector quantity as constant, then right, its direction should also be constant and its magnitude should also be constant. Then right, that vector quantity can be constant. But here, if the velocity is not changing, it means its magnitude is getting constant. On the circular path is direction is getting continuously changed, right? Its direction is getting continuously changed. So it means if direction is getting changed, right, it is a change for a vector quantity. So that's why I've written magnitude of the velocity is constant, direction changes, speed is constant. So the first noteworthy point related to the uniform circular motion, tangential acceleration is 0. There is no acceleration that can increase or decrease the velocity. If this acceleration is present, right, either it can be in the direction of velocity or it can be in the opposite direction of velocity. Suppose if it is in the direction of the velocity, then obviously it is going to increase the velocity. Suppose it is in right opposite direction of the velocity, then obviously it is going to decrease the velocity. So it means that according to the definition of centripetal acceleration, if velocity is going to increase, it means centripetal acceleration is going to increase, right? If velocity is going to decrease, it means centripetal acceleration is going to decrease. So that's why reason that if tangential acceleration is 0, then we are forming the situation that is a uniformly acceleration, the uniformly circular motion. Now, apart from this, if I'm talking about the linear momentum, same, magnitude constant, direction changes. Now if the tangential acceleration is getting 0, then in the uniform circular motion we are having only one kind of the acceleration, that is centripetal. So what you want to write for the centripetal acceleration, right? Obviously magnitude of the centripetal acceleration is constant. Why? Because the velocity is not changing, direction is changing. How direction is changing? Suppose if I'm talking about to the 4 points, right, onto the circular path. Okay, here the direction of the centripetal acceleration is towards left, it is towards downwards, this is towards right, and this is upwards, right? So according to the sign conventions as was we are following, this is positive I, this is negative I, this is positive J, right, and this is negative J. So these are the some, see, the students are having that kind of the misconception, right? Okay, in between the magnitude and the direction of this important physical quantities. How velocity is getting constant, right? No, its magnitude is getting constant. How acceleration is getting constant? No, the magnitude of the centripetal acceleration is getting constant. How momentum is getting constant? No, how the magnitude of the linear momentum is getting constant. Direction of the all quantities are getting changed. What about the position vector? It is also getting changed. Right now, this was the details and the noteworthy points related to the uniform circular motion. Everything will get into the notes. Now what about the analysis? See, in analysis for the uniform circular motion we saw the noteworthy points. Now we are moving forward to the most important term, right, to the most important two shortcuts. As I said before, in between the 2 points, let us take an example, in between A to C, right, particle is getting displaced and we are having a angular displacement. As I said, magnitude of the velocity is constant, but the direction is changing. It is a vector quantity. It means if direction is changing, the quantity is getting changed. How that change you are going to calculate between any 2 points onto the circular path? How the change in R, that is the position vector, how the change in velocity, how the change in acceleration we are going to calculate. How? Because all of those R, V, A, they all are the, what we can say, this quantities, now vector quantities. Now for vector quantity to be constant, the direction should remain constant, even that magnitude should remain constant. But here only the magnitude is getting constant and direction is changing. It means the quantity is changing. 3 important shortcuts are there, right? This spatially should happen on the circular path, right? And this formulas, this shortcuts are only applicable for the uniform circular motion, not more than that. These are only applicable for the uniform circular motion, right? Suppose the particle is moving right from point A to point B, making the angular displacement of theta. At A, the velocity of the particle is defined as this way. At B, the velocity of the particle is defining like this way, right? Can I rearrange those vectors, right? This is VA, this is VB. The resultant of them will be according to the law of vector addition. The resultant of them, right? What we saw, this is the first vector, this is the second vector, so this one is the resultant, right? Okay, this is the first vector, this is the second vector, this is the first vector, this is the second vector, so we can write first vector plus second vector, that is equal to resultant vector. Same the thing we are going to rearrange for this, right? The same thing we are going to rearrange for this, right? How? Let's see this stuff. Right? Okay. What will be the resultant for V and VB? VA square VB square plus 2VA VB cos of theta, where theta is angle between these two vectors, right? Theta is angle between these two vectors, right? Now magnitude at this 2 point is completely same, so change in velocity vector we can define it as, right, V square plus 2V square cos of theta. So change in velocity vector will be 2V square plus 2V square cos of theta. So this will be 2V square 1 plus cos of theta. I am using the double angle formula that you use in trigonometries. So from here we are getting delta V, that is equal to 2V square into 2 sine square theta by 2. So the change in velocity vector is defined as 2V sine of theta by 2. The change in velocity vector is defined as, right? Now how I am going to rearrange those terms? Law of vector addition. If change in velocity is determined by this equation, then obviously we are having another shortcut for change in, see, suppose here, right, we got the what we can say the equation of change in velocity, but here the centripetal is in this direction, even centripetal is in this direction. The radius vector, it is in this direction, here the radius vector is in this direction, right? So the position vector is getting changed, the acceleration vector direction is getting changed, right? In all the parameters having the constant magnitude, but the directions are getting changed. So in that state, for delta R, I am going to write directly it as delta R sine theta by 2. It's not sine whole theta by 2, it's sine of theta by 2. It's sine of, right, theta by 2. Similarly, for change in acceleration is 2a sine of theta by 2. So these are the, right, three most important shortcuts. Those are who are, right, these are the three most important shortcuts that are used in, right, uniform circular motion. Okay, these are the three most important factors that are used into the uniform circular motion. Three most important equations, right? This is equation number 1, right? Okay, same procedure you need to follow for 2 and 3. Right, same procedure, right, you need to follow for 2 and 3. So this is a detailed analysis into the most important formulas for the circular motion. Now first, if the particle is moving on the circular path, what is the formula of centripetal acceleration? We got it as V square by R. What is the formula for a time period of a revolution? Time period of a revolution, right? Can I write it as omega, that is equal to delta phi by delta t? Can I write it as omega, that is equal to delta phi by t? Omega 2 pi by, or in another sense, let's move on to the most simple time period of the revolution, right? And that will be, don't waste the time, right, directly write the formula, right? Because on the circular path we are having V is equal to R omega, V is equal to R into theta by time, right? And this time, that is equal to theta into R for V. This is an actual formula for time period, right? This is an actual formula of time period, but this is for one revolution. Right? Okay, so we are having this formulas only, right? Not more than this two formulas, 3 formulas, and this one. These are enough for the uniform circular motion. There is one exceptional case in which work energy theorem is also used in the uniform circular motion, but that kind of this stuff we are going to see into the work energy chapter, right? That kind of stuff we are going to see into the work energy chapter. So this was the uniform circular motion. Now let's move on to the next part of non-uniform circular motion, what it states, right? Non-uniform circular motion. Let us see again, okay, the example. Particle is there at t is equal to 0, it is starting its motion, right, from position A, right? At t is equal to 0, it is starting its right motion, right, from position A. Now, in the non-uniform circular motion, the tangential acceleration is non-zero. Tangential acceleration is non-zero. It means that either the first possibility, either if the velocity is acting in this direction, so the tangential acceleration may act in this direction, right? By having so, what will happen? This will increase the velocity of particle. Second case, suppose the velocity is on the circular path is like this way and tangential acceleration is like this way. So this will decrease the velocity of particle. This will decrease the velocity of the particle, right? Tangential acceleration. Now, what will be the formula? See, now it is changing the velocity. Now, either it is increasing or it is decreasing. It is changing the velocity. Now, it means that tangential acceleration is actually defined as how the velocity of a particle, right, on the circular path is changing with respect to time. That's the concept of the tangential acceleration. So in the non-uniform circular motion, we are having the 2 to 3 simple formulas. 2 to 3 simple formulas on which directly questions into the NEET and JEE kind of examinations are been, right, asked. Say, one, we are having the equation of the tangential acceleration. Yes, right, that is equivalent to dv by dt. Second, I am having the another equation, right, centripetal acceleration, that is v square by r. If for a non-uniform circular motion, we are having the two kind of the acceleration. So is it possible the particle is responding to both? Yes, it is possible that particle is responding to both. How? The particle is moving with net acceleration. What is the net acceleration of the particle? Suppose if I'm talking about at position A, centripetal is acting into the negative I direction plus tangential is acting into the positive J direction. So the net acceleration at point A, right, it will be negative of v square by r of I plus dv by dt of J into the vector form. And suppose if you want to write down the magnitude, then magnitude of the net acceleration, right, it will be, right, v square by r, right, whole square plus dv by dt, right, whole square. This will be the magnitude of the, right, net acceleration of the particle if it is performing the non-uniform circular motion. So in non-uniform circular motion, basically we are having 2 to 3 terminologies. In non-uniform circular motion, basically we are having 2 to 3 terminologies, and that we are going to discuss it right now. Okay, this is one of the visualization, okay, but it's okay, it's not a big deal, right? The most important formulas, right, okay, in the case of the non-uniform circular motion. Again, let us take a circular path. This is the center, right? Particle at t is equal to 0, right? It is at the position A. Right, we are having two kind of the acceleration. The first one, that is centripetal acceleration acting this side. Second, right now I am taking it as into the direction of the velocity, else there is a possibility it may, right, oppose the velocity also. So the first most important formula, that is, right, the formula of net acceleration, right? Here we are having the formula of the velocity vector is here only, and this is the position vector r. Okay, so the net acceleration, as I said, that is equivalent to rod, okay, the centripetal acceleration square plus, right, tangential square. So that will be, right, v square by r, right, whole square plus dv by dt square. The first most important formula, right? The second, what angle the net acceleration is making with respect to velocity vector. What angle, right, the net acceleration, right, makes with velocity. Suppose this is a right net acceleration, right? Okay, one, that angle, right, net acceleration is making either with velocity or tangential acceleration. Second, the angle it is making with the radius vector or centripetal acceleration. If I am defining those angles, one as theta, second as phi, then tan theta we can say it as centripetal whole divided by tangential, that is v square by r whole divided by dv by dt. And the second most important formula, that is tan of phi, the angle between the net acceleration and centripetal or the radius, that is equivalent to, right, tangential by centripetal, the reverse of that, that's dv by dt whole divided by v square by r. So this is the analysis and the complete formulas of the non-uniform circular motion, right? The analysis and the complete formulas for the non-uniform circular motion, right? Okay, so now let's move on. Let's have the glimpse of the circular motion so that we can move on to the sums related to it. Okay, see. First of all, right, in circular motion, what we did, right, okay, we had a, what we can say, the simple definition of the circular motion. What are the examples, right, of the circular motion into our day-to-day life? What is the responsible thing for the circular motion, right? That is the centripetal. See, till now we haven't dealt with the centripetal force, because in AIMS, I think in 2018 or 17 in AIMS, right, one question was asked into the non-uniform circular motion related to force, right, and work energy theorem, W is equal to delta K, that term, that formula, right? But that we are going to say into the work energy theorem, right? Because right now we are not dealing with the force, we are only dealing with, right, with the kinematics. We are not dealing with the cause of, right? So this was a circular motion. After that we moved on to the terminologies and we saw the visualizations related to the, right, circular motion. And after that, right, we moved on with the uniform circular motion and the relevant shortcuts and the relevant formulas. And after that we moved on with the non-uniform circular motion and the relative analysis and their formulas, right? Now let's move on to the sums, right, of the uniform circular motion and non-uniform circular motion. So as we have seen as we all have seen the concepts of the uniform circular motion, non-uniform circular motion, let's solve the sums related to it. Okay, so two particles A and B, they are moving in the uniform circular motion in circles of radius RA and RB with speeds VA and VB. One is moving with the radius of RA like this way, second for the radius of RB. One is having the magnitude of velocity as VA, second is having the velocity of the magnitude VB. Now they both are moving in such a way that their time periods are equal. The time period of the rotation is same, right? Both. Sorry. Time period of the rotation is same. It means that time period of the first particle, that is equivalent to time period of second. Right, so can I replace this at 2 pi by omega of A, 2 pi by omega of B. It means both are having the same angular velocity. Both are having the same angular velocity. So it means that the ratio of the angular velocity will be 1:1. Right? NEET 2019. The question has been asked into the NEET 2019. Okay. Now let's move on to the next question. Particle starting from rest moves into the circle. This is a case of the non-uniform circular motion, and one new equation we are going to use. Right? Particle starts from rest. It is like moving following the circumference of the circle. It is starting from rest. After some time, it is gaining the linear velocity of v0 after n rounds. After completing n rounds, it is gaining. Starting from rest. After completing n rounds, it is gaining the velocity of v0. Then what will be its angular acceleration? Odisha NEET 2019. Right? So guys, I've been moving aside, right? If you need to, if you want to solve this question, right? Okay, I'm giving you the 5 seconds. You can pause the video and solve this stuff. right? You can pause the video and solve this stuff, right? So it's 5, 4, 3, 2, 1. See, suppose it starts from rest. So when I say initial angular velocity is 0, initial velocity is 0 meter per second, radian per second. Now what will happen here? Final it is gaining. So I'm using the third equation of the motion. Omega square minus omega 0 square is equal to 2 alpha theta. Okay, this equation I haven't taught you, but you all are aware of this. For rotation, we are using this equation if angular acceleration is constant. Right? If linear acceleration is constant, we are using this equation as v square minus u square is equal to 2as. So analogy you all are aware of. Right? So final velocity is omega, initial is 0, 2 alpha. Now it is completing the n rounds. In one round, theta is 2 pi. In n rounds, theta will be 2 pi into n. So alpha will be omega square whole divided by 4 pi of n. Right? Suppose it is a circular motion, can I replace alpha as v square whole divided by 4 pi of n r square? So this will be the angular acceleration of the particle, right? Or v0 square. Okay, C is the perfect answer for this specific question, right? C is the perfect answer for this specific question. I'm moving aside if you think you want to take a snap of it. Okay, now let's move on to the next. This is a very nice question. This is asked in NEET phase 2 2016. In a given figure, if the acceleration of the 15 meter per second square represents the total acceleration of the particle moving in clockwise direction, this A represents the total acceleration of the particle. Radius is given as 2.5. What will be the speed of particle? So I'm moving aside. If you really want to solve this, I'm giving you all the 5 seconds to solve this stuff, right? 5. You can even pause the video, right, and solve this. First of all, I'm giving all the 5 seconds. You can 5, 4, 3, 2, 1. So in the given figure, suppose if A is a total acceleration, A is having the two components. One is this direction, that is A sine of 30. One is in this direction, right? A cos of 30. So A cos of 30 will provide the necessary centripetal acceleration, and because of that, particle is moving on the circular path. So again I replace it as v square by r. So v square, that is equal to, right, A into cos 30 root 3 by 2 into r. So I'm replacing all of those values. So we are getting v square is equal to acceleration is 15 root 3 by 2 into r is 2.5. V will be approximately equivalent to 5.7 meter per second. C will be the perfect answer. V will be approximately equivalent to 5 meter per second. The C will be the perfect answer for this specific question, right? Let's move on to the next one. A particle is moving with the moves in a circle of the radius 5 centimeter. Radius is 5 centimeter. Time period is 0.2 pi seconds. The acceleration of the particle is a very simple here. It is a case of the uniform circular motion asked in IIT examination of 2011. Right? Okay. So T is equal to 2 pi r by V. This is equation number 1. Right? So from this we are going to find V, that is 2 pi r by T. So this is 2 pi. Radius is 5 centimeters. So 5 into 10 to the power minus 2 whole divided by time, it is 0.2 pi seconds. So this is going to cancel, right? And this will be 10 to the power minus 1, right? And this is going to be plus 1. So this will be 5 into 10 to the power minus 1. Velocity will be 0.5 meter per second, right? But what we need to calculate, we need to calculate the acceleration. Acceleration, that is equal to v square by r. So A will be 0.5 into 0.5, right? Acceleration, radius is 5 into 10 to the power minus 2. So real acceleration, we are getting it as 5 meter per second square. Okay, after delivering all of those concepts, this thing is that much easy at what you are thinking. Yes, it can be solved within less than a minute, right? D is a perfect answer. This question, I'm giving you all the homework, right? Guys, please don't get so much worried because we are doing less question in this session, because this session is going to be like for approximately 5 hours. It is going to extend for 5 hours, right? So I don't think so that much amount of the time you're going to sit in front of the screen, right? So don't get so much worried. Whenever you are downloading this PPT session, the PPT of this session, right? Okay, so in that case, some extra sums are already available. This is what I'm showing you in front of all those who are easily solvable, and then we can easily correlate it to the concept, right? And apart from this, some of the questions I've given you in the homework, and many of the questions are real also available into whatever the presentation it is there, and you are going to download from the app. Okay, so I think this was for the circular motion, okay, for the uniform and non-uniform. Now let's move on to, see, concept is all in front of you. Okay, now let's move on to another part, that is the concepts of the relative motion, right? So let's move forward, right after moving on to the some of the important sums related to the circular motion. Now let's move forward to the most important concept of the relative motion. In our previous lecture, we already discussed, right? I already told you all that relative in 1D and 2D, right? I'm going to discuss in the all of those stuff into the same lecture only. And there are, apart from this, right, apart from the fundamental logic, right, there are some of the applications of the relative motions like Riverman problem, Rainman problem. We are going to see some of the question solving approach for this kind of the problem also, right? In some of the cases, there is a direct approach we are going to see, right? Okay, so first of all, let's move on to the basics of the relative motion, right? What it states, right? What it states. See, there are lots of technical definitions of the relative motion, but if right, if I want to write one in front of you all, that motion of an observer with respect to another observer. Motion of an observer with respect to another observer, right? Is it not for sure, right, that we are having only one kind of the observer who is analyzing the motion, right? It is not for sure there exists only one scientist, right, who has the power to discover the same concept. No, right? Okay, we can have the multiple observers also, but right, what does the relative motion states? I'm going to show you all one example in front, right? That will be, right, quite easy for you all to understand this concept, right, fundamentally. Okay, so motion of an observer with respect to another observer. You can see into the visualization. First, observer is in hot air balloon. Second, the observer, right, is in sea. How motion appears to the person who is inside the hot air balloon. How the motion appears to the person inside the hot air balloon. How the motion appears to the person who is moving into the sea. Motion of one observer. The very, as I said, lots of technical definitions of the relative motions are there, right? We are not dealing to that much, right? Lots of things are there, but the thing that is easily understood by you all, that is in front. Motion of one observer with respect to another observer. How? See, this is object A, this is object B. One is object A, second one, that is object B, right? Second one, that is object B. Now, this is B and this is A. A is moving with velocity of VA. B is moving with velocity of VB. I am taking three observers. First, the observer is on ground. In our previous session also, and in this beginning of this session also, as I said, right, motion is nothing without observer. Okay, in universe, I can't say for any particle that it is on the absolute rest. I can't say for any particle that it is in absolute motion. Everything is just a frame of reference. Everything is just about an observer. Basically, two types of the frame of references are there. One that is an inertial frame, second that is a non-inertial frame. We are going to discuss that detail again in this, right, within just few minutes of this, right, okay, after this discussion, right, within few minutes we're going to discuss that part, right, how frame of references differs, how motion is going to change, right. So I'm taking the three observer. The first one, right, that is standing on ground, the second one that is standing on A, and the third one that is standing on B. These are the three observers, right? These are the three observers. So I want to ask you all, is analyzing, see, activity, the phenomena is quite simple. A and B are moving. But we are analyzing this activity from three different perspectives. We are analyzing this activity from the three different perspectives. Simple phenomena. A and B, they both are moving with the different velocities. One is moving with VA, second is moving with VB with respect to ground. Three observers. Is it possible that this activity is same for all? Whether it is on the ground, whether the observer is on A, well, it's on B. Is it possible that it is same for all? The answer is no. It's not same for all. Right? It's not same for all. Suppose let us take an example. VA is greater than VB. First, for the observer on ground, we are analyzing the activity from the three different perspectives, three observers, right? The position of the three observers has already been mentioned, right? The foreign observer on the ground, particle A is moving with velocity VA, B is moving with the velocity VB. Why? Because the observer on the ground is having, right, zero frame velocity. It is having zero frame velocity. So that's why I'm considering this observer or this frame as inertial frame. Always you are going to see, right, the reality from the inertial frame. Right, if you want to see the actual if you want to see the reality from the non-inertial frame, then there is a need of the pseudo force, and that part is going to come into the, right, the next session. So here, if we are, say, observer is saying A going, A is moving with the velocity A, VB is moving with, I'm stationary. You are analyzing me, you are analyzing me, okay, you are an observer, right, I'm another observer, okay, we are understanding the concept of the relative motion. You are an observer, I am another observer, okay. Let us take a very simple example. You are sitting in front of me, yes, you are sitting in front of me. Are you stationary? I'm asking you all. You are stationary? Yes. If you are stationary, I am stationary, right? You are absorbing, you are an observer and analyzing my activity. Right now, somewhere you are sitting into the room and stationary, okay. Now, particle is moving with the velocity VA. You will be the inertial frame because you are stationary and you are analyzing a particle that was moving with the velocity. Right? So you were able to see the reality. Now let's move on to the another part. Suppose this recorded lecture, okay, you are seeing somewhere, right, in flight. Oh, it's a 4-hour long flight. Oh, let's see this lecture of physics of Indrajeet sir, right? Suppose if you are doing so, moving with the velocity V. So right now the particle is also moving, one observer is also moving with the velocity, right? Okay, and you, the actual person who is analyzing the activity, it is also having some velocity. So are you going to see the same reality that you were about to see from the ground frame or from the inertial frame? No. Suppose if you are moving into the train, is it possible that you are going to analyze, you are going to have the same output? No. So for observer 1, yes, A is moving, wow, B is moving, wow. Second, for observer on A, VA is greater than VB. I am A, somewhere is behind is B. I am A, B, right? Anna? Observer is on A. So what is velocity of A with respect to observer A? 0. Because if I am on, the observer is on A, the observer is having the same amount of the velocity that object A is having, right? So from a relative perspective, these two are stationary with respect to each other, not with respect to ground. They are stationary. If I am inside the train and train is moving with the 100 km/h speed, right? So it means if I'm inside the train, I am also moving with 100 km/h, but with respect to ground. But with respect to train, I am stationary, right? Because you both are moving, whenever the two objects are moving with the same speed, so relatively they both are at rest with respect to each other, not with respect to ground. So if observer is on A, then he is stationary with respect to A. A is stationary with respect to observer because they are both are moving with the same velocities. But what will be the velocity of B with respect to A? If the observer is on A, B is beside it. A velocity of A is more as compared to B, right? Now how motion, see how motion of A and B is appearing to the observer on ground. A is moving, B is moving. How the motion, right, of both particles, right, is appearing to the observer on A. Yeah, A is stationary, but B, it is moving backward. It is moving into the backward direction. It is moving far away. Why? Because velocity of B is less than A. So VBA, it means what? Velocity of B with respect to A. With respect to A, it means this is an observer. A is an observer, right? With respect to A, it means that A is an observer. Right, with respect to A, it means that A is an observer. Now let's move on to the most important part. For observer on B, now I am in B. A, what will be the velocity of B with respect to B? 0. If I am standing on B, they both are moving with the common velocity. Hey, the observer is telling to that object, hey, you are relatively at rest with respect to me, not with respect to ground. But what will be the velocity of B with respect to A? Sorry, what will be the velocity of A with respect to B? Because observer is B, na? What is velocity of A with respect to B? That is VA minus VB. Now how motion appears to the observer on B? A is moving away. One activity is going on, but you can analyze how it is getting different if the observer is changing its position or the frame, right? The observation point is getting changed. The things are getting changed. For, see, we are again I'm just piling up this thing into the very summarized form, right? I'm analyzing an activity in which two objects are moving. One it is moving with VA, one it is moving with VB with respect to ground. For an observer on ground, how the activity, how the phenomena appears, A is moving, B is moving with the respective velocity. For an observer on A, how the phenomena appears, A with respect to observer is at rest. but B is moving away because VB is less than VA. How this activity appears to be for an observer, those who is on B is at relatively rest with respect to object, right? But for with respect to A with respect to A is moving away. For observer B, A is moving away. Why? Because speed of A is greater than B. So this is what the relative motion is, right? Analyzing the motion, right, from the another observer and another perspective, right? So whenever we are having, like, whenever it is written, right, that is VB with respect to A, it means velocity, right, of object B, right, with respect to observer A. If it is written velocity of A with respect to B, then we can write it as velocity of A, right, okay, with respect to observer B. In this case, we can write it as VB minus VA, right, or in this case, we can write it as VA minus VB. Is it clear for you all? Is it clear? Right. So this is an actual concept of the relative velocity. This is the actual concept of the relative velocity. Okay. So now this was a detailed analysis. Now let's move on to the question solving approach. Right. Basically, right, everything depends on the frame of references. Right. Everything depends on frame of references. Now what is a frame of reference? That I'm going to show you all in front. The point from which observer is taking its observation is a frame of reference. Basically, there are two types of frame of references. The first one, that is an inertial frame of reference, right? The second one, that is a non-inertial frame of reference. For inertial frame of reference, right, the frame velocity, right, is 0 or frame velocity is constant with respect to object. Right? Non-inertial frame velocity, right, is not equal to 0. Either it is increasing or it is decreasing. So that is known as the non-inertial frame of reference, right? That is known as what? Non-inertial frame of reference. Okay. So from frame of reference perspectives, everything's are getting changed. Suppose, let us take an example. Again, this is B, right? This is A, right? With respect to the observer on ground, he is moving with the velocity VA and he is moving with the velocity B. What will be the actual question solving approach? Right? Same thing we are going to see here, right? Okay. This is A, right? This is B. Object is moving with velocity VA. This is moving with the velocity VB, right, with the right observer on the ground. What will be the question solving approach for all kind of the relative motions concepts, right? What will be the question solving approach, right? And what are the applications? See, right now this thing we are going to see, we are saying into the 1D only. Okay. Suppose, first of all, step 1, check whether acceleration of 1 with respect to 0 or whether this condition is getting satisfied or not, right? Either acceleration of 1 with respect to 2 is getting 0, right, or 1 with respect to 2 is not equal to 0. Two possibilities may arise, right? If 2, let us take an example. Suppose this is moving with 10 meter per second velocity and this is moving with the 20 meter per second velocity, then just you have to check it out, right? Whether there is any kind of the relative acceleration between two particles or not. Whether they are having any kind of the relative acceleration between two particles or not. Step 2. If A12 is equivalent to 0, either A12 is equivalent to 0 or A21 is equivalent to 0. Anyone among two can be the observer. in relative motion, right, it completely your choice which observer you want to take from all of those perspectives, right. Okay, the answer is going to be right same if you are considering, if you're avoiding the sign conventions. So if a12 is equal to 0 or a21 is equal to 0, it means the relative acceleration, right, between the object is 0. It means it is a case of a relative uniform motion. In the case of relative uniform motion, we are having only one equation. Velocity of one with respect to two is displacement by time. Only one equation we are going to use in this stuff. Now let's move on to the second possibility. Suppose if a12 is not equivalent to 0 or a12 that is equivalent to constant, then it is the case of relative uniformly accelerated motion. So in this case, we are going to use the three equations of the motion, right? Okay, in this case, right, we are going to use the three equations of the motion, right? The first equation of the motion would be what? I'm extremely sorry, right? As of the high visualization, it is happening. V1 of 2, that is U1 of 2 plus A1 of 2 into T. S1 of 2 is equal to U1 of 2 plus half A1 of 2 into T square, right? V1 of 2 square minus U1 of 2 square is equal to 2A1 of 2 S1 of 2. Right, this is the concept of the relative, right, motion. Okay, so this should be the question solving approach, right, for the relative motion. Okay, so the first step in all of those cases of the relative, all of those numericals of the relative motion, we need to just check it out, right, whether the relative acceleration between the particles is 0 or not, right? Okay, from any particle frame of reference, either 1 with respect to 2 or 2 with respect to 1, right? From either frame of reference, the relative motion of the particle, right, is 0 or not. If it is 0, right, then it is a case of the relative uniform motion. Only one formula we are going to use. If it is non-zero, right, or it is constant, right, then it will be the case of the relative uniformly accelerated motion. And the three equations of the motions, right, we are going to use the relative motions perspective, right? Like v12 that is equal to u12 plus a12t, s12 that is equivalent to u12t plus half a12t square. Like this way the equations are mentioned. So this is only the question solving approach, right? Okay, again I am writing into the summarized form. If it is like relative, okay, uniform motion, um stands for uniform motion, then we are having only one equation, right? v12 that is equivalent to s12 whole divided by time, right? Okay, and second, that is a relative uniformly accelerated motion. Relatively uniformly accelerated motion, that is if in this case a12 that is equivalent to constant, right? And for this we are using the three equations of motion. F v12 that is u12 plus a12 into t, s12 that is equal to u12 plus, right, sorry, u12 t, okay, plus half a12 t square, and the third equation of the motion, right? Okay, this kind of the stuff. This is only the two question solving approaches are there. Okay, now let's move on to the next part, right, of the relative motion. I think due to the high visualization, okay, this is moving on, right? Okay, see, there are the two most important applications of the relative, okay, motion. The first one, that is a riverman problem, and second, that is a rainman problem. Apart from this, right, they are having, right, the aeroplane wind problem, car flag problem, all are, right, completely based on the relative motion only, right? All are based on the relative motion only, right? Nothing more than that. Okay, so let's move on to the stuff, I think, as of the visualization. So students, we have already seen the concepts of relative motion in 1D. For relative motion in 2D, right? Obviously the Riverman and Rainman problems are going to come. First of all, let's solve some of the sums related to 1D as according to the question solving approach what I gave in front of you. Okay, see. Preeti reached the metro station. Okay, this question has been asked in NEET 2017. So it's a very simple. We have to just find whether the particle both of among two, any one of or either two, right, they are getting accelerated or not. That's it. This was only the simple question solving approach, right, that we have seen. See, okay, see this one, relative acceleration is 0 or not. That's it. Okay, we are following this case only. We are going to follow this case only and we're going to solve this sum, right? Okay, see, Preeti reached the metro station and found that escalator was working. She walked up the stationary accelerator in time t1. Distance is d. She walked up stationary accelerator in time first. Velocity of Preeti was 0, right? Velocity of escalator was v. On another days, if she remains stationary on moving, okay, escalator was not working. She walked up. Sorry, she walked up. I'm sorry. She walked up. Right, velocity of escalator was 0, right? Okay, velocity of escalator was 0 and this was v meter per second. It takes time t1. On another days, if she remains stationary, in second case, velocity of the Preeti is 0. The escalator takes up in time t2. So velocity of accelerator is something. Let us take an example. It's v meter per second. Then the escalator takes her in time, then time taken by her to walk on the moving escalator. See, in all of those courses, d is constant. Step 1, we need to check it out, whether the escalator is getting accelerated or not, whether the Preeti is getting accelerated or not. So as mentioned into the question, no one is getting accelerated, right? So it means we are going to use this equation, right? V1 with respect to 2, that is equal to S1 with respect to 2, T1 with respect. Right? Okay. Now, suppose first case, she walked up with speed v1, escalator is stationary, right? So it means, can I say relative, that is equal to v t whole divided by t1. Second case, right? Okay, see, this is v1 d by t1. In second case, she was stationary, escalator was moving. Let us take an example, its speed is v2. So in second case, escalator was moving, so can I say d by t2. In third case, right, okay, by her to walk up, time taken by her to walk up on the moving escalator. Now both are moving. So if both are moving, then obviously the relative velocity will be v1 plus v2, right? So that will be d whole divided by time t. So can I replace d by t1 plus d by t2, that is equal to d by 2. So time, this will be equivalent to t1 t2 whole divided by t1 plus t2. Why I added here? According to the concept of the relative velocity, if the velocities are in the same direction, then it should get subtracted. But why I added here? There is a difference, right? Okay, fundamental logic differs. How it differs, right? See, it's a very simple thing. If I am, see, if the water is still, I am moving, I am having some velocity. If I am stationary, water is flowing, then I am having the velocity of the water. But if water is also flowing and I am also, right, acquiring some, I am also applying, I am giving some velocity to it, then obviously, right, the velocity, the resultant velocity will be get added. The magnitude of the resultant velocity will be get added. So that's why I added it, right? So B will be the perfect answer for this specific, right? Now, let's move on. A bus is moving with the speed of 10 meters per second on the straight road. This is a bus. It was moving with speed of 10 meters per second on the straight road. From the bus at the distance of 1000 kilometers, there exists a scooterist, right? A scoot, he wishes to overtake the bus in 100 seconds, right? Then with what speed he needs to move on, right? This question is asked in 2009. So guys, I'm moving aside. If you want to, right, pause the video, you can just pause the video, right? Or if you want to just solve it, right, you can just pause the video and solve it. I'm giving you the 5 seconds. 5, 4, 3, 2, 1. The bus and scooters, they both are moving into the same direction. First of all, what we need to check, any one among two is getting accelerated or not. No one is getting accelerated, so acceleration of one with respect to 2 is 0. So this is a case of relative uniform motion. Velocity of 1 with respect to 2, distance 1 with respect to 2, time. Distance 1 with respect to 2 is 1000 kilometer, time is 100. So it's 1000 whole divided by 100 is equal to 10. So relative velocity of 1 with respect to 2 is 10. So V1 minus V2, that is equivalent to 10. So what is the velocity of the scooter? That is 10 plus 10, 20 meter per second. Right? D is a perfect answer for this specific question. The simple example of the relative motion. Simple example of the relative motion. Okay. Let's move on to the next sum. A train of, see, this is all what about 1D we are going on, relative in 1D. Train of 150 meter length is going towards the north at the speed of 10. Train, right, 150 meter. Okay, it is moving towards the north, right? I'm sorry, it is moving towards the north, right? This train is moving, right? The length of the train is 150 meter, right? And it is moving towards the north with the speed of 10 meter per second. So velocity of train with respect to ground is 10 meter per second. Parrot flies in the south, means opposite direction of it. This is the velocity of parrot with respect to ground, 5 meter per second. The time taken by the parrot to cross the train. First step, you have to check it out whether one is getting accelerated or not. No one is getting accelerated, so this is a case of the relative uniform motion. So what we are going to have, it's very simple thing, as V1 with respect to 2, that is S1 with respect to 2 time. Now both velocities are in opposite direction, and in the case of the relative motion, according to the conventions, they will be get added. Right? So this will be 10 plus 5, that is equal to distance 150 meter whole divided by time. Time will be 150 whole divided by 15. It will be equivalent to 10 seconds. D will be the perfect answer. So that much simple relative motion is after the explanation. Two train, each of 50 meter long. See, 3 examinations, CPMT 1999, JIPMER 2000, RPET 2001. Two trains, each 50 meter long, are traveling in opposite direction with velocity 10 and 15. Time of crossing is what? This is one train, 50 meter long. This is another train, right, 50 meter long. They both are traveling into the opposite direction, obviously on the different parallel tracks, right? I have drawn, it is not the same, it is on the different parallel tracks, right? One is having the velocity of 10 meter per second. One is having the velocity of 15 meter per second. Obviously, the relative acceleration of both is 0. It means it is a case of relative uniform motion. It is a case of relative uniform motion. Now, how much amount of the distance? It is a case of the relative uniform motion, and V12, that is S12 by T. The velocities are both into the opposite direction, so it means it will be get added. So it's 10 plus 15. What will be the relative distance covered? 50 while they while moving inside, and 50 to cross each other. 50 while moving inside, 50 to cross each other. So total distance will be 100. Right? So T will be 100 by 25. Right? T, that is equal to 4 seconds.
B is the perfect answer
for this question. Okay. So guys, this is a homework from my side. So this were all of the sums related to, right? This were all sums related to the motion, relative motion in one day. Now, we are going to move forward on the concepts of Riemann problems, the Riemann problems. They are actually the questions related to the relative motion. They can be represented in vector, right? Okay, all of those stuff we are going for. Okay, so guys, let's move on to this. Let me allow to drink some amount of the water because it's already the one of the most important applications, right? The one of the most important applications, right, of this one, the relative motion. See, relative 1D and 2D, right, are one and the same thing, right? Okay, in just 2D, okay, the vector representation is there. Okay, so if moving on to the third if moving on to the third session of an 11th syllabus, right, now you are able to differentiate between what actually the motion in 1D is on the rectilinear path, right, or what the motion in 2D is. Okay, so now let's move on to the most important problem, that is a Riemann problem, right? These two are the one of the most important applications, right? These two are the one of the most important applications, right, of the relative motion. Now, okay, see, Riemann problem, right, it is depending on only one simple concept, right, and one simple thing. Now what actually it is, right, we are going to see, right, okay, there is only one approach. Okay, see, Riemann problem. Okay, see, suppose, okay, see, all of those Riemann problem, Riverman problem, they are completely based on the right concepts of relative motion 2D only. Okay, suppose if I'm talking about the first part, initially, right, man is having zero velocity with respect to ground, right? Man is having zero velocity with respect to ground, right? Velocity of a rain with respect to ground, right? Let us take an example as v, meter per second. Okay, velocity of rain with respect to ground, that is equivalent to v, meter per second, right? Now in this case, okay, man is standing, it's raining vertically, right? Man is standing, it's raining vertically. What will happen, right? A simple statement I am writing. What will happen if man starts running at speed v1 meter per second? If he is standing, rain appears to him. How? What he is saying, that is most important part, right? Okay, the most important part in this kind of the problem is how rain appears to men. How rain appears to men, right? What actually is going on? Suppose he is standing, right? Rain appears to him that drops are falling vertically, right? Suppose in another case I'm talking about he is moving, then what will happen, right? Rain will be get drifted at some specific angle, right? So in second case, suppose this is a ground, right? If man is moving on with the speed of, right, v meter per second, when he was standing, the drops were, right, falling vertically, the rain appears to man as like falling, right, vertically. But when he is moving with some speed, right, rain, right, appears to be like drifted at some angle, right, tilted at some angle theta with respect to vertical. Simple form, he is standing, right, rain appears to be falling vertically, right? He is moving, rain is tilted at some angle theta with respect to vertical. In both of the cases, right, it is important how rain appears to man. how it appears when he was standing, how it appears when he is moving with velocity, how it will appear when the particle, the man, will increase its velocity, how it will appear when he suddenly stops. Suppose let us take a very simple example of our day-to-day life, right? A very simple example, right, of our day-to-day life. Okay, it states that, right, suppose I'm standing in front on my bike. Okay, suddenly, right, it starts raining. Okay, so when I was just about to accelerate the bike, right, my initial velocity was 0, right, suddenly it started raining. So how it appeared to me when my initial velocity was 0, it was falling vertically. Now suddenly, by seeing that scenario, I accelerated my bike and immediately moved on. Now I am gaining some velocity. So how rain appears to me as falling, like it appears like tilted at some angle with respect to. First it was appearing like it was falling like this way, right, when I was stationary. When I when I will move with some velocity, it will like fall directly in front of me like that at some angle with respect to vertical. It will see, when I'm stationary, it is appearing like this way. When I'm moving, it will appear like this way, tilted at some angle with respect to vertical, right? So it is important, right, how rain appears to the man. Okay, now we are going to solve this sum, right, using, okay, the same concept only. How? Just remember this thing, how rain appears to man. Okay, so let's see some of the sums related to it. First, suppose, first case, when man was standing, velocity of man with respect to ground was 0. Velocity of man with respect to ground was 0. The rain appears to fall vertically at the speed of 10 meter per second. Suppose man starts running at the speed of, let us take an example, 10 meter per second, right? So my question is, at what angle he needs to hold the umbrella while moving? When he was standing at the rest, rain appears to be falling vertically. Now suppose when he is moving with 10 meter per second, right? Okay, then at what angle he needs to hold the umbrella? As I said before, simple concept, we need to focus on how rain appears to the man. In this case, how rain appears to the running man. What will be the velocity of rain with respect to man? That will be velocity of rain with respect to ground minus velocity of man with respect to ground, right? This actually is the question of relative 2D. Right? Why it is a question of relative 2D? Right now everything is going on to the single level, surface level only. But after this, right, we're going to see some of the important sums, right, in which actually I, J, all kind of the directions will be included, right? Okay, so this is just the first step at the beginners level. After that, we will move on to the sum, right? Okay, a bit. Okay, after that, again, I will do some changes and do modifications, right, to understand the concept well, right? So now, how rain appears to the man? How rain appears to the man? Velocity of rain with respect to man. Observer is man. So velocity of the rain with respect to man. What is the velocity of rain with respect to ground? Okay. As usual, I said you all that for sign conventions, we are considering the very simple term, right? This will be considered as a positive. Vector in this direction will be considered as a positive. Vector in this direction will be considered as negative. Vector downward, that is considered as positive, and vector upward, that is considered downward as negative, upward as positive. So rain, obviously it is right, falling downward. So can I say it is negative of 10 of J? Man is moving towards the right side, so obviously it will be 10 of I. So this is how rain appears to the man. Let's plot the vector. Okay, suppose let us take an example. This is a ground. The man was running with the 10 meter per second square. How the rain is appearing, right? How the rain is appearing. Okay, I'm sorry for that. See, negative of 10 of I, negative of 10, negative of 10. Resultant of this two, this is how the rain is appearing to the running man, right? This is how the negative of 10I, okay, negative of 10J, okay. Now, this is how the rain is appearing to the running man. Now, he wants to save himself, right? Okay, he wants to save himself from the rain. So that's what has we have asked into the question, at what angle he needs to hold the umbrella with respect to vertical. Suppose the rain appears to the running man like this way, so anti-parallel to this, right? We need to hold the umbrella. Anti-parallel to this, right? We need to hold the umbrella, making angle phi with respect to vertical, right? This is my umbrella, right? Making angle phi with respect to vertical, right? We have to hold the umbrella like this way, right? So here we are having 10 of phi, that is equivalent to, see, suppose if this is phi, then we are having this of phi, so that is equal to negative of 10 by negative of 10. If we need to calculate this angle, then we need to do the ratio of this by this, right? If we need to calculate this angle, then ratio will be this by this. This is a very simple vector notation and the basic concept of vectors, right? Okay, so here we are getting phi as 45 degree, right, with respect to vertical, right? So at 45 degree with respect to vertical, right, he need to hold the umbrella. Suppose I was standing, right, rain was right falling at 10 meter per second. Suppose I started moving with 10 meter per second. So at 45 degree I need to hold the umbrella. Why? Because rain appears to the running man like at 45 degree with respect to vertical. So anti-parallel to this, I need to hold the umbrella to save myself from the rain, right? Anti-parallel to this, I need to hold the umbrella to save myself from the rain, right? So this was the first question of the rainman problem. Okay, now let's move on to the most important next sum. Suppose again, okay, doing some modification into the previous sum. See, whatever we did right now, I'm doing some modification in this. Suppose was man, initially man was stationary, velocity of man with respect to ground was 0, right? And the rain was 10 meter per second. It was falling vertically, tilted at some angle. This was the velocity of rain with respect to ground at 10 meter per second, making 30 degree with respect to. This was the initial scenario when man was standing, its velocity with respect to ground is 0. In previous case, we considered when he was standing, his velocity with respect to ground was 0, rain was falling vertically. But now, when its velocity with respect to ground is 0, the rain is already tilted at some angle. So if I'm standing, rain is already tilted. So if I will move, the rain will again, right, okay, it will, what we can say with respect to this vertical, the angle will be tilted more, right? So suppose let us take an example, right? The particle, the man with respect to ground starts moving with 10 meter per second, right? 10 meter per second. Suppose it starts moving with 10 meter per second, right? Okay, okay. Then at what angle with respect to, right, vertical, okay, a man needs to hold the umbrella. Okay, same, at what angle with respect to vertical, okay, man needs to hold the umbrella, right? Again, in the same question, we need to focus on the simple concept how rain appears to the running man. Okay, so again I want to just write down a very simple, very few statements, right? Velocity of rain with respect to man, that is equivalent to velocity of rain with respect to ground minus velocity of man with respect to ground. Now, when man was standing, what was its velocity? It was having the two component. This is VRG cos of 30, right? This is VRG sine of 30, right? So this is equivalent to, can I say, phi root 3, and this is equivalent to phi. So what this vector is? This vector can be represented as, when man was standing, the velocity of rain with respect to ground is negative of phi I, negative of phi root 3 of j. Same, I have to write it here. Says negative of phi of I, negative of phi root 3 of j. Right. Now, what is the velocity of the man with respect to ground? It is moving right with the velocity of 10. So can I write it as 10 of I? Yes. So finally, how rain appears to the man with the vector as negative of 15 of I, negative of phi root 3 of j. Right. But this is how rain appears to the man. We got that. But at what angle, right, a man should need a hold the umbrella, that we need to calculate. Okay, let's plot this vector on the Cartesian coordinate system, right, to get the answer. Okay, suppose it's negative of 15i. It's negative of 15i and negative of phi root 3 of j. Negative, that's why we have taken 15 into the left side, and phi root 3 negative, that's why we have taken into the downward direction. So this will be, right, the velocity of rain with respect to man, right? Okay, now anti-parallel to this, we need to hold the umbrella. Anti-parallel to this, right, we need to hold the umbrella. So this will be the angle. So suppose if this is the angle, then right, this will be the angle. If suppose this is the angle, then this will be y, this will be x, right? So this will be negative of 15 by negative of phi root 3. So this will be 10 of phi, right? Phi 3 are, right? Negative, negative will be positive. Okay, it's root 3. At 60 degree, he needs to hold the umbrella, right, with respect to vertical. At 60 degree, he needs to hold the umbrella with respect to vertical. At 60 degree, he needs to hold the umbrella with respect to vertical, right? Okay, so now see, first see, everything is depending on everything depends on this simple statement, how rain appears to the man. Okay, in first we saw when he was standing, velocity with respect to ground was 0, rain was falling vertically, suddenly started moving, rain appears to be tilted at some angle, then at what angle he needs to hold the umbrella, right? So we calculated. After that, right, we saw initially when he was his velocity with respect to ground was 0, rain was already tilted at some angle. So when he starts moving with some velocity, right, then he was again, so this was a velocity, right, when man was standing, right, when velocity of man was 0, right, and this is, okay, the another angle, right, 60 degree, right, when velocity of man with respect to ground is 10 meter per second, right? You can just see. Now let's move on to the third most important sum, right? Okay, this is the sum I'm going to give you in front of you all, and after that we are going to see the riverman problems. All of those arrangement problems are going to solve like this way only. Okay, now suppose, okay, if the man is standing here, right, velocity of man with respect to ground is 0. Velocity of man with respect to ground is 0. Okay, the rain appears to be falling, right, with a magnitude of 10 meter per second, making 30 degree with respect to vertical. Now, suppose man starts moving with the velocity of 10 meter per second on inclined plane, making angle 60 degree. Velocity of man with respect to ground, that is equal to 10 meter per second, making theta is equal to 60 degree with respect to horizontal, right, with respect to horizontal. Now at what degree he needs to hold the umbrella? what angle he needs to hold the umbrella. First question, man was standing, rain was falling downward, right? And when he moves, rain was tilted at some angle. In second case, we saw man was standing, rain was already tilted at some angle. When he starts moving, then at what angle? Now in third, right, we tilted the observer. Man was standing, rain was falling at some angle. When the man is already moving on an inclined plane, what will happen? Same procedure we need to calculate, right? Velocity of rain with respect to man, anti-parallel to this, right? Okay, anti-parallel to this. Okay, man needs to hold the umbrella. Right, anti-parallel to this, man needs to hold the umbrella. So this is a homework from my side, right? I will be waiting for this stuff, right? I will be waiting for all of those answers, right? Okay, I will be waiting for all of those answers, right, into the comment box beneath the video, right? Okay, now, okay, let's move on to the next part, that is the riverman problems. Okay, see, riverman problems. There is only, see, as in rainman problems, right, there was a single approach of an observer. In a rainman problem, there was a single approach of an observer, how rain appears to the running man. Similarly, right, the riverman problem is also having the one solving approach. Right, basically maximum number of the question into the riverman problems, they are going to come from only two cases, right? And for those, right, directly shortcut I'm going to give. Apart from these two cases, right, there is a possibility of the third case, right? We are going to discuss that also, right? Don't get so much worried. But basically, right, maximum number of the questions are coming from the two cases and one single approach that we are going to discuss right now. Okay, even you can just check out all of those PYQs where you're going to, right? Okay, this question solving approach will help you a lot. Okay, now see, riverman problems. Now what it states, see, it's all about, right, it's all about, okay, this is the width of the river. Right, a man standing at the one point of the river he needs to reach to the another point. Man standing at the one point. This is what a relative 2D I'm discussing about. Riverman and rainman problems, right, they are completely based on the relative 2D. Relative 1D, right, it is very simple, upstream, downstream, right? It is very simple case. So, right, we are not discussing that much, right? We are directly moving on to the most important stuff today. Simple case. He needs to start from A, right? And he needs to reach to the opposite side. For this, he is having the two possibilities. If man swims with a flow, if man swims with a flow, if man, see, suppose let us take an example, right? This is the velocity of a river with respect to ground. The first case, suppose he want to, right, reach to the opposite side, right, and he is moving, right, supporting the flow, then he can reach into the opposite side into the minimum time. Right, suppose if these two things we are going to discuss into the detail, don't get worried. Suppose a man swims with a flow, then obviously he is going to reach into the opposite side into the minimum time. Suppose he restricts the flow, right, he is going to cover minimum distance, and that is the width of the river. Two cases, either he is moving with flow, either he is restricting the flow. right? Now how these two cases, right, are applicable, how these things will go on, right, we are going to discuss that in detail. But this is an actual scenario of the riverman problem. But what is the question solving approach in this? Always this is a question solving approach, as like I've given into the rainman problems, how rain appears to the man, like this for all kind of the riverman problems, right? Always analyze situation from ground, right, or inertial frame, right, not from river. Always keep observer on ground, whatever it is happening on the ground, right, whatever observer is seeing from the ground is the reality, and it is only the way to solve this kind of this stuff very easily, right? It is only the way, right? It is only the way to solve this kind of the sums easily. Now let us take an example, right? Let us take an example. Okay, see, first case, right? This was a question solving approach. Okay, case 1, minimum time. I'm directly giving you all the shortcuts for this. First is the case of, right, minimum time, right? It is a case of the minimum time, right? Now suppose let us take an example, right? Man starts from A and he needs to reach to the opposite bank. B is the width of river, right? Now suppose this is velocity of river with respect to ground. Now what happens here? Okay, first of all let us take two observers. First, that is observer on ground. Second, the observer is man himself. First, the observer on ground. Second is the observer man himself. Now suppose river is not flowing. Suppose velocity of river with respect to ground is 0. It's a still river. Water is still. I'm man. Starting. I started with A. I will reach to B. If it's a still water, I will start from A. I will reach to B, exactly to the opposite, and if the water is still. Now what will happen? Suppose if I start from this point and river is flowing. So according to another observer into the river, let us take another observer into the river. According to him, I am trying to move forward by closing my eyes, but river is trying to drift me. I am moving forward, river is trying to drift me. I am moving forward, river is trying to drift me. I am moving forward, river is trying to. So actually, with respect to river, inside the river, I am trying to push myself forward by swimming. With respect to river, I am trying to push myself, I am trying to swim myself forward in the forward direction. Is it the reality? No. Why? River is flowing. What will be the reality? It has been seen by the observer who is on ground. With respect to river, the swimmer is continuously trying to flow. It appears to the man who is swimming that he is moving forward, but actually river is trying to drift him. So with respect to ground, with respect to the man in the river, he is trying to swim forward. So that's why he is giving the velocity with respect to river forward. But what actual the reality is? What actual the reality is? River is trying to drift. So this reality has been seen by observer on ground, and that will be velocity of man with respect to ground. Actually, with respect to river, he is trying to swim forward, but river is trying to drift. River is drifting him, right? So here comes the actual results, the actual reality. He is not moving in forward direction, but it is moving in due to the drift of a river, right? So in this case, what will happen? He will move. He will reach to the opposite side of the bank, right? But extra, he will reach by this procedure, right? He will reach in minimum time, but right, he will reach into the minimum time, right? But we will have the extra drift. Okay, but we will have drift. Case is over. This drift is D. What reality the observer on ground is seeing? What reality the observer on ground is seeing? He is moving at some angle theta. Let's draw the triangle. This is the width of the river. This is the drift width. This is the angle, right? This is velocity of man with respect to ground. Why? Because with respect to the observer on ground, man is moving into the tilted manner. This is velocity of man with respect to river. This is velocity of river with respect to ground. Simple triangle. You will get your answers. First, suppose it is making 90 degree. Can I write sine theta as, suppose this is D, this is B. Can I write it as D square plus B square? Right? So sine theta, that will be VR of G whole divided by Vm of G, and that will be equivalent to D whole divided by under root of D square plus B square. A simple math. Suppose if I'm writing on cos theta, then we are having Vm of R whole divided by Vm of G, that is whole B whole divided by D square plus B square. Right. Third case. Suppose if I want to write tan theta, right, then it will be VRG whole divided by, right, Vm of R, that is D by B. Why I wrote this, all of this shortcuts? Whatever the amount of the data is given, just select the correct equation, resolve it. Whatever the data it is given, just select the correct equation, resolve it. Whatever the data it is given, just select the correct equation and resolve it. One another question is asked in this: minimum time. Minimum time. Okay. Time has no relation with relative motion. It is fixed from all observers' point of view. As I said before, suppose if the observer is changing its position, then obviously the scenario is getting changed. We have discussed all of those examples. But in all of those frame of references, time is always constant. Time is not going to change. Time is constant. It means that, right, the value of the time from any frame of reference never changes in an activity. So suppose if time is constant and if you are having, right, the value of drift, then you can write it as by VRG. Suppose if you are having the width of the river, then you can have VMR. Suppose you are having right, under root of D square plus B square, then you can write it as VMG. Okay, this is the way to calculate the minimum time, right? This is the way to calculate the minimum time. Okay, and this will be, okay, VMG, right? So this is the formula of time, minimum time. Apart from this one, another question has been asked: what is the length he covered? This was the width of the river. This was the external drift he faced. He was about to reach at this point, right? This was the width of the river. This was a drift he faced. But what actually length he covered while swimming in the journey is this, right? Actual length covered while swimming in journey, that will be under root of d square plus b square. So here the case 1 is completely over, case of minimum time, right? Those who are missing any single point in this concept, right, I must suggest you all to rewind this video and see this. All of those questions are coming from this part only, right? You have to just find out VRG, whatever the data is given, just apply. Whatever the data is given, just apply this stuff, right? Now let's move on to the second case, that is a case of minimum distance, right? Minimum now, suppose again this is a river, right? This is the width of a river B. In first case, right, man feels like, right, he was dumped. Man feels like, right, he felt like being frauded by someone. So this time he decided he wants to start from A and compulsory wants to reach to B. He wants to start from A and needs to compulsory reach on B. So at that time, what will happen? So this time he said that, suppose if the river is moving with this velocity, this is the velocity of river with respect to ground, and he was decided and he was smart also. So he decided, I want to move. First I was moving right forward with respect to river, and a river frauded him by drifting to some else position. So this time he decided, I will try to jump at some angle with respect to vertical. Then what river will do? River will drift him. He is moving at some angle, river will drift him. He is moving at some angle, river will drift him. He is moving at angle, river will drift him. So what? He is trying to move in this way, right? He is trying to move right in this way, but river will drift him. And he will actually move in this way to reach at the opposite end B. Again, I am taking two observers, one observer on the ground and one observer inside the river. With respect to ground, say with respect to the man on river, he is moving like this way. In the previous case, he was moving into the forward manner, but right now with respect to the man on river, he is moving like this way, tilted at some angle theta. Right? So this is velocity of man with respect to river. But actually how he is moving with respect to the observer on ground, straight to reach to the opposite end. With respect to the man on river, he is moving like this way, but river is drifting him. He is moving like this way. Sorry, he is moving like this way, river is drifting him. He is moving like this way, river is drifting him. So to reach to the opposite end, right? Obviously, suppose he is having the scenario, he was about to have the extra drift, but it didn't happen. It was about to have extra drift. This kind of the terminologies are used in this question. He was about to cover right that much drift, but it didn't happen. Again, same in this case, we are having one triangle, right, and same formula, right? Again, in this case, we are having a triangle, right, and the same formula. What? This will be the triangle, right? This will be the theta, right, and this will be VRG, right, this will be VMG, right, this will be VMR, right, okay, and this will be what we can say B. This will be about to have extra diff. This is the length he is covering with respect to observer on river. Again, simple. If I'm talking about this is a 90 degree, right, then sine theta, that will be equivalent to VRG, right, okay, whole divided by VMR. Similarly, it will be D whole divided by under root of B square plus D square. Okay. Okay. Similarly, cos theta, that is equivalent to VMG whole divided by VMR. That is equivalent to, right, B whole divided by under root of B square plus D square. And finally, okay, the tan theta, okay, that will be equivalent to VRG, right, whole divided by VMG, and that will be equivalent to D by B. Time of journey, from all of those perspective, time is constant. So if you are taking D, then it should be VRG. If you are taking B, then it should be VMG, right? And if you are taking under root of D square plus B square, then it should be VMR. Whatever the data is given, just apply this question, right? So this is the case of the minimum distance for the riverman problem. Now there exists the third case. Is it not so possible that it is always possible while swimming at some angle theta with respect to vertical, he is always going to reach point B? Is it possible? Always. In some cases it is possible, but in some cases it might not. So what happens here in the third case, right? Suppose he want to start at A, he want to reach at B. Suppose a river is flowing with respect to ground. Now he starts, right? He starts, this is a velocity of man with respect to. Now velocity of man with respect to river is quite less, right? He is applying less like internal energy, right? Okay, he is gaining some less velocity inside the river to reach the B. Or in another sense, velocity of the river is quite high. In this case, what will happen? He will not exactly reach to the point B, to the opposite point, but he will drift somewhere here, right? Okay, in that case, this will be the extra drift he will cover, right? So in that case, what will happen? This will be the theta, right? This will be the drifting angle, right? And this will be the width of river. So in this case, what we need to do? Simple. Velocity of man with respect to river, velocity of man with respect to ground minus velocity of, right, river with respect to ground. That's it. Your question will be solved, right? And suppose this is an extra drift he covered. If you need to calculate the length of the journey, this is not having any kind of the shortcut formulas, right? Okay, suppose this is the length of the journey, right? Then it will be under root of B square plus D square. So this much, right? This will be B, this will be D, and this will be the length of the journey, right? Okay, there are some ways to calculate this theta also and this phi also, right? Okay, because in that case it has been asked with respect to vertical how much, right, he is tilted, and lots of things are there, but everything is coming from this question only, this part only. So this is a third special case, right? Okay, this is a third special case. Okay, so this was the riverman problem. Now let's move on to the some of the important problems related to it. So students, we have seen the concepts of the relative 2D. Now we are going to solve the sums in it. The speed of the swimmer in the still water is 20 meters per second, right? The speed of the river in water is 10 meters per second and flowing due to east, right? Okay, see, this is a river. Speed of the river, it is given as with respect to ground, that is equal to 10 meters per second, and it is flowing through east, right? Speed of the swimmer, okay, see, he needs to cross into the shortest path. Directly it is given as a shortest path. So we are going to use this stuff. River with respect to ground is given, right? This is given, okay, this is a speed of a man with respect to river, that is 20 meter per second it is given. This is velocity of man with respect to ground. This is theta. Directly we are going to use this triangle, and this question has been asked in 2019. So whatever the special cases I've given, right, those are quite helpful. Okay, so yeah, directly sine theta, that will be equivalent to VR of G whole divided by VMR. This is what we have written, na, VRG by VMR. See, we are using this formula. Whatever the data is given, use that formula, right? Okay, so that will be 10 by 20. So theta, that will be equivalent to, right, sine inverse of half. Theta will be 30 degree. So this angle we are getting in the 30 degree, right? This will be north, this will be south, this will be east, and this will be west. So our answer will be 30 degree west. B is the perfect answer. The angle at which he should make his stroke with respect to north. He has to make his stroke with respect to north, right? So it's 30 degree west, right? It is a terminology. If this is a theta, right, then it is 30 degree west, right? That kind of the terminology is there. Okay. Now this one, the width of the river is 1 kilometer. The velocity of the boat is 5 kilometer. This is the first case. It has been asked in 2019. The port cover the width of the in the shortest time. Okay. Width is 1 kilometer. Right. The velocity of the boat is 5 kilometer per hour. This is velocity of man or boat with respect to ground, velocity of river with respect to ground, velocity of man with respect to river. This is the theta, right? The same first concept we are going to use, right? The same, which one? This is the first case, right? This formula we are going to use. Okay, this triangle we are going to use. Okay, so now let's move on to the sum. Okay, so the minimum time formula. If I'm talking about the width 1 kilometer, then its speed is VMR. If I'm talking about the drift, that is D, then that is VRG. And if I'm talking about under root of D square minus B square, right, then it is VMG. Okay, first of all, by using this, I'm going to calculate the VMR. VMR, that will be equivalent to 1 kilometer whole divided by 15 minutes, right? So 15 whole divided by 60, it's 1 by 4. VMR, that will be equivalent to 4 kilometer per hour. Right, so using this formula we got, right, the velocity of the man with respect to river. Now we need to calculate velocity of river with respect to ground. This is given as 5 km per hour. So if you're following the triangular law of vector addition, can I easily write down VRG square plus VMR square is equal to VMG square? Right, we can use the triangular law, and even if I'm considering RG vector and MR vector, then angle between them is 90 degrees. Simple vector law of addition, right? So VRG square, that will be 25 minus 16 VRG, that will be equivalent to 3 km per hour. A is the perfect answer for this specific question, right? So apart from this, okay, I'm giving you all, some questions are already present, and even you can download this presentation, right, on the app. Okay, some questions I have already keep this for your homework, right? You can answer all of those questions right into the comment box beneath the video. So guys, obviously it was a very long lecture, but obviously, right, we were having the like enormous amount of the ample amount of the concepts in front. So guys, I think thanks a lot for the teaser, right, and even thanks of the lots for the love that you showered into the previous video, right? I will be waiting for all of your comments, right, regarding this lecture, right? I want all of your comments right beneath the video, right? Okay, I want all of your comments beneath the video. So guys, it's time to go, right? Again, we will come back with a new teaser, with a new session of the Newton's law of motion with a short period of time. So guys, this is Indrajeet Singh signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side, Bacha ji. Bye everyone. Stay at home, stay safe, stay healthy. Chemistry point away. Bye.